van a buscar seguramente cientos o quizás miles de empleados. Acá seguramente no van a mostrar qué es lo que están buscando, pero acá simplemente pon tu nombre, tu mail y la carta. Acá lo que yo pondría es:
The need is an up-gearing linkage system that converts the force into velocity at the end effector of our heels for purposes of giving to the human body agility. So this is one of the main things that are amazing about the human body. And I'm concluding my part at this point, and I would like to welcome my colleague Mike, who is going to talk to you about hand design. Thank you very much.
Thanks, Konstantinos. So we just saw how powerful a human and a humanoid actuator can be. However, humans are also incredibly dexterous. The human hand has the ability to move at 300 degrees per second. It has tens of thousands of tactile sensors, and it has the ability to grasp and manipulate almost every object in our daily lives.
Hasta ahora lo que pasó en el evento es revisaron un poco el sistema de navegación de los que tienen en los autos Tesla y lo mostraron cómo actúa en el robot. Mostraron un sistema de simulación 3D que me pareció muy bueno, pero es un poco parece como si estuviera procesado offline. Si estuviera procesado online, lo pueden hacer igualmente con más poder. Y después están mostrando el hardware, que está muy bueno para una versión 1. Nada que no se haya visto, pero explicaba Elon Musk que lo que pueden hacer ellos es producirlo en masa. Y eso es muy bueno porque permite el proceso de mejora. En primer lugar, en cuestión de software, hay que ver cuánto le dejan hacer a uno con el robot en su casa. Por ahora están como reclutando gente de todas las áreas de la robótica, incluido el software, para mejorarlo, supongo, bastante.
One of the important aspects of our hand is that it's adaptive. This adaptability is involved essentially as complex mechanisms that allow the hand to adapt to the objects that's being grasped. Another important part is that we have a non-back drivable finger drive. This clutching mechanism allows us to hold and transport objects without having to turn on the hand motors. You just heard how we went about designing the Tesla bot hardware. Now I'll hand it off to Milan and our autonomy team to bring this robot to life.
Thanks, Mike. All right. So all those cool things we've shown earlier in the video were possible just in a matter of a few months.
Va a ser prometedor si tiene continuidad.
Most of those components ported quite easily over to the bot's environment. If you think about it, we're just moving from a robot on wheels to a robot on legs. So some of the components are pretty similar, and some other require more heavy lifting. So for example, our computer vision neural networks were ported directly from autopilot to the bot's situation. It's exactly the same occupancy network that we'll talk into a little bit more details later with the autopilot team that is now running on the bot.
Esa parte que muestra un overlay verde arriba de las personas no me gusta mucho porque eso es tagging. Y el tagging dinámico es, o sea, dinámico o asincrónico es 2D. O sea, eso lo taguea gente a mano y aunque el robot se dé cuenta, es 2D. Y el mundo no es 2D, entonces no me gusta el proceso ese.
Another interesting problem to think about is, in indoor environments, mostly with that sense of GPS signal, how do you get the bot to navigate to its destination? Say, for instance, to find its nearest charging station. So we've been training more neural networks to identify high-frequency features, key points within the bot's camera streams, and track them across frames over time as the bot navigates through its environment. And we're using those points to get a better estimate of the bot's pose and trajectory within its...
O sea, el poder que tiene es que al producir muchas unidades van a empezar a escanear el mundo y a generar data, mucha data. Tagueando objetos individualmente, o sea, objetos cotidianos que la gente tiene en su casa, no sé, celulares, cositas que uno va teniendo en su casa, estos robots los van a incluir al software y ese es como el gran poder que tiene a full absolutamente.
Start accelerating as we unlock more joints and deploy more advanced techniques like arms balancing over the past few months.
Mucho tagueo a mano, millones de taggers.
That's very different as we're moving from the car to the bots environment. And so I think it warrants a little bit more depth, and I'd like my colleagues to start talking about this now.
Thank you, Milan. Hi, everyone. I'm Felix. I'm a robotics engineer on the project, and I'm going to talk about walking. Walking seems easy, right? People do it every day. You don't even have to think about it. But there are some aspects of walking
Ojalá mencione algo de
from engineering
que
perspective.
sea predictivo
For example,
acerca de hacia dónde va su cuerpo cuando se mueve.
self-awareness. That means having a good representation of yourself. What is the length of your limbs? What is the mass of your limbs? What is the size of your feet? All that matters. Also, having an energy-efficient gait. You can imagine there's different styles of walking, and all of them are equally efficient. Most important, keep balance, don't fall. And of course, also coordinate the motion of all of your limbs together. So now, humans do all of this naturally, but as engineers or roboticists, we have to think about these problems. And therefore, I'm going to show you how we address them in our locomotion planning and control stack. So we start with locomotion planning and our representation of the bot. That means a model of the robot's kinematics, dynamics, and the contact properties. And using that model and the desired path for the bots, our locomotion planner generates reference trajectories for the entire system. This means feasible trajectories with respect to the assumptions of our model. The planner currently works in 3 stages. It starts planning footsteps and ends with the entire motion for the system. And let's dive a little bit deeper in how this works. So in this video, we see footsteps being planned over a planning horizon, following the desired path. And we start from this and add then foot trajectories that connect these footsteps using toe-off and heel stride, just as humans do. And this gives us a larger stride and less knee bend for high efficiency of the system. The last stage is then finding a center of mass trajectory, which gives us a dynamically feasible motion of the entire system to keep balance. As we all know, plans are good, but we also have to realize them in reality. Let's see how we can do this.
Muchas veces se ven los robots que caminan con la fuerza que ponen en los actuadores y en las piernas y no hacen mucho equilibrio ni nada. Y eso era lo sorprendente de Boston Dynamics, que como que jugaba con la inercia y eso. Y eso es software y sensores, y me imagino que puede haber mucho trabajo en el desarrollo de sensores que tengan esa parte, la parte de la lógica del software integrada en el hardware directamente, para que el feedback no sea todo procesamiento, porque la prioridad de todos los procesamientos, eso es muy difícil de manejar y lo tiene, o sea, cada potencial de movimiento tiene que ser contemplado previamente y priorizado o con algún mecanismo de decisión de priorización de cuál vector tiene más importancia y proyectar ese vector hacia el futuro. Entonces es software y es complejo.
Vibrations and modes, compliance, sensor noise, and on and on and on. So what does that do to the real world when you put the bot in the real world? Well, the unexpected forces cause unmodeled dynamics, which essentially the planner doesn't know about, and that causes destabilization, especially for a system that is dynamically stable like biped locomotion. So what can we do about it? Well, we measure reality. We use sensors and our understanding of the world to do state estimation. And state estimation, here you can see the attitude and pelvis pose, which is essentially the vestibular system in a human, along with the center of mass trajectory being tracked when the robot's walking in the office environment. Now we have all the pieces we need in order to close the loop. So we use our better bot model, we use the understanding of reality that we've gained through state estimation, and we compare what we want versus what we expect that reality is doing to us in order to add corrections to the behavior of the robot. Here, the robot certainly doesn't appreciate being poked, but it does an admirable job of staying upright. The final point here is a robot that walks is not enough. We need it to use its hands and arms to be useful. Let's talk about manipulation.
Hi, everyone. My name is Eric, robotics engineer on TeslaBot, and I want to talk about how we've made the robot manipulate things in the real world. We wanted to manipulate objects while looking as natural as possible, and also get there quickly. So what we've done is we've broken this process down into 2 steps. First is generating a library of natural motion references, or we could call them demonstrations. And then we've adapted these motion references online to the current real-world situation. So let's say we have a human demonstration of picking up an object. We can get a motion capture of that demonstration, which is visualized right here as a bunch of keyframes representing the locations of the hands, the elbows, the torso. We can map that to the robot using inverse kinematics. And if we collect a lot of these, now we have a library that we can work with. But a single demonstration is not generalizable to the variation in the real world. For instance, this would only work for a box in a very particular location. So what we've also done is run these reference trajectories through a trajectory optimization program, which solves for where the hand should be, how the robot should balance during when it needs to adapt the motion to the real world. So for instance, if the box is in this location, then our optimizer will create this trajectory instead. Next, Milan's going to talk about what's next for the Optimus Tesla bot. Thanks.
Thanks, Eric. Right, so hopefully by now you guys got a good idea of what we've been up to over the past few months. We started having something that's usable, but it's far from being useful. There's still a long and exciting road ahead of us. I think the first thing within the next few weeks is to get Optimus at least at par with Bumble C, the other bot prototype you saw earlier, and probably beyond. We're also going to start focusing on the real use case at one of our factories, and really going to try to nail this down and iron out all the elements needed to deploy this product in the real world. I was mentioning earlier, indoor navigation, graceful fall management, or even servicing, all components needed to scale this product up. But I don't know about you, but after seeing what we've shown tonight, I'm pretty sure we can get this done within the next few months or years, and make this product a reality and change the entire economy. So I would like to thank the entire Optimus team for all their hard work over the past few months. I think it's pretty amazing. All of this was done in barely 6 or 8 months. Thank you very much.
Hey, everyone. Hi, I'm Ashok. I lead the autopilot team alongside Milan. God, it's going to be so hard to top that Optimus section. We'll try nonetheless. Anyway, every Tesla that has been built over the last several years, we think has the hardware to make the car drive itself. We have been working on the software to add higher and higher levels of autonomy. This time around last year, we had roughly 2,000 cars driving our FSD beta software. Since then, we have significantly improved the software's robustness and capability that we have now shipped it to 160,000 customers as of today. Thank you. This did not come for free. It came from the sweat and blood of the engineering team over the last 1 year. For example, we trained 75,000 neural network models just last 1 year. That's roughly a model every 8 minutes. That's coming out of the team and then we evaluate them on our large clusters, and then we ship 281 of those models that actually improve the performance of the car. And this pace of innovation is happening throughout the stack. The planning software, the infrastructure, the tools, even hiring, everything is progressing to the next level. The FSD beta software is quite capable of driving the car. It should be able to navigate from parking lot to parking lot, handling city street driving, stopping for traffic lights and stop signs, negotiating with objects at intersections, making turns, and so on. All of this comes from the camera streams that go through our neural networks that run on the car itself. It's not coming back to the server or anything. It runs on the car and produces all the outputs to form the world model around the car, and the planning software drives the car based on that. Today, we'll go into a lot of the components that make up the system. The occupancy network acts as the base geometry layer of the system. This is a multi-camera video neural network that from the images predicts the full physical occupancy of the world around the robot. So anything that's physically present, trees, walls, buildings, cars, balls, what have you, it predicts, if it's physically present, it predicts them, along with their future motion. On top of this base level of geometry, we have more semantic layers. In order to navigate the roadways, we need the lanes, of course. But then the roadways have lots of different lanes, and they connect in all kinds of ways. So it's actually a really difficult problem for typical computer vision techniques to predict the set of lanes and their connectivities. So we reached all the way into language technologies, and then pulled the state of the art from other domains, and not just computer vision, to make this task possible. For vehicles, we need their full kinematic state to control for them. All of this directly comes from neural networks. Video streams, raw video streams, come into the networks, go through a lot of processing, and then outputs the full kinematic state, like positions, velocities, acceleration, jerk, all of that directly comes out of the networks with minimal post-processing. That's really fascinating to me, because how is this even possible? What world do we live in that this magic is possible, that these networks predicts fourth derivatives of these positions, when people thought we couldn't even detect these objects? My opinion is that it did not come for free. It required tons of data, so we had to build sophisticated auto-labeling systems that churn through raw sensor data, run a ton of offline compute on the servers. It can take a few hours, run expensive neural networks, distill the information into labels that train our in-car neural networks. On top of this, we also use our simulation system to synthetically create images. And since it's a simulation, we trivially have all the labels. All of this goes through a well-oiled data engine pipeline, where we first train a baseline model with some data, ship it to the car, see what the failures are. And once we know the failures, we mine the fleet for the cases where it fails, provide the correct labels, and add the data to the training set. This process systematically fixes the issues. And we do this for every task that runs in the car.
Yeah, and to train these new massive neural networks, this year we expanded our training infrastructure by roughly 40 to 50%. So that sits us at about 14,000 GPUs today across multiple training clusters in the United States. We also worked on our AI compiler, which now supports new operations needed by those neural networks, and map them to the best of our underlying hardware resources. And our inference engine today is capable of distributing the execution of a single neural network across two independent systems on chips, essentially two independent computers interconnected within the same full self-driving computer. And to make this possible, we had to keep a tight control on the end-to-end latency of this new system. So we deployed more advanced scheduling code across the full FSD platform.
All of these neural networks running in the car together produce the vector space, which is again the model of the world around the robot or the car. And then the planning system operates on top of this, coming up with trajectories that avoid collisions, are smooth, make progress towards the destination, using a combination of model-based optimization plus neural network that helps optimize it to be really fast. Today, we are really excited to present progress on all of these areas. We have the engineering leads standing by to come in and explain these various blocks, and these power
not just the car, but the same components also run on the Optimus robot that Milan showed earlier. With that, I welcome Paril to start talking about the planning section.
Hi all, I'm Paril Jain. Let's use this intersection scenario to dive straight into how we do the planning and decision making in Autopilot. So we are approaching this intersection from a side street, and we have to yield to all the crossing vehicles. Right as we are about to enter the intersection, the pedestrian on the other side of the intersection decides to cross the road without a crosswalk. Now, we need to yield to this pedestrian, yield to the vehicles from the right, and also understand the relation between the pedestrian and the vehicle on the other side of the intersection. It's a lot of these intra-object dependencies that we need to resolve in a quick glance. And humans are really good at this. We look at a scene, understand all the possible interactions, evaluate the most promising ones, and generally end up choosing a reasonable one. So let's look at a few of these interactions that Autopilot system evaluated. We could have gone in front of this pedestrian with a very aggressive longitudinal lateral profile. Now, obviously, we are being a jerk to the pedestrian, and we would spook the pedestrian and his cute pet. We could have moved forward slowly, shot for a gap between the pedestrian and the vehicle from the right. Again, we are being a jerk to the vehicle coming from the right, but you should not outright reject this interaction in case this is only safe interaction available. Lastly, the interaction we ended up choosing: stay slow initially, find the reasonable gap, and then finish the maneuver after all the agents pass. Now, evaluation of all of these interactions is not trivial, especially when you care about modeling the higher order derivatives for other agents. For example, what is the longitudinal jerk required by the vehicle coming from the right when you assert in front of it? Relying purely on collision checks with marginal predictions will only get you so far, because you will miss out on a lot of valid interactions. This basically boils down to solving a multi-agent joint trajectory planning problem over the trajectories of ego and all the other agents. Now, how much ever you optimize, there's going to be a limit to how fast you can run this optimization problem. It will be close to order of 10 milliseconds, even after a lot of incremental approximations. Now, for a typical crowded, unprotected lift, say you have more than 20 objects, each object having multiple different feature modes, the number of relevant interaction combinations will blow up. The planner needs to make a decision every 50 milliseconds. So how do we solve this in real time? We rely on a framework what we call as interaction search, which is basically a parallelized tree search over a bunch of maneuver trajectories. The state space here corresponds to the kinematic state of ego, the kinematic state of other agents, their nominal future multimodal predictions, and all the static entities in the scene. The action space is where things get interesting. We use a set of maneuver trajectory candidates to branch over a bunch of interaction decisions, and also incremental goals for a longer horizon maneuver. Let's walk through this tree search very quickly to get a sense of how it works. We start with a set of vision measurements, namely lanes, occupancy, moving objects. These get represented as sparse abstractions as well as latent features. We use this to create a set of goal candidates, lanes again from the lanes network, or unstructured regions which correspond to a probability mask derived from human demonstrations. Once we have a bunch of these goal candidates, we create seed trajectories using a combination of classical optimization approaches, as well as our network planner, again trained on data from the customer fleet. Now, once we get a bunch of these seed trajectories, we use them to start branching on the interactions. We find the most critical interaction. In our case, this would be the interaction with respect to the pedestrian, whether we assert in front of it or yield to it. Obviously, the option on the left is a high penalty option. It likely won't get prioritized. So we branch further onto the option on the right, and that's where we bring in more and more complex interactions, building this optimization problem incrementally with more and more constraints. And the tree search keeps flowing, branching on more interactions, branching on more goals. Now, a lot of tricks here lie in evaluation of each of this node of the tree search. Inside each node, Initially, we started with creating trajectories using classical optimization approaches, where the constraints, like I described, would be added incrementally. And this would take close to 1 to 5 milliseconds per action. Now, even though this is a fairly good number, when you want to evaluate more than 100+ interactions, this does not scale. So we ended up building lightweight queryable networks that you can run in the loop of the planner. These networks are trained on human demonstrations from the fleet, as well as offline solvers with relaxed time limits. With this, we were able to bring the runtime down to close to 100 microseconds per action. Now, doing this alone is not enough, because you still have this massive tree search that you need to go through, and you need to efficiently prune the search space. So you need to do scoring on each of these trajectories. Few of these are fairly standard. You do a bunch of collision checks, you do a bunch of comfort analysis, what is the jerk and axle required for a given maneuver. The customer fleet data plays an important role here again. We run 2 sets of, again, lightweight queryable networks, both really augmenting each other. One of them trained from interventions from the FST beta fleet, which gives a score on how likely is a given maneuver to result in interventions over the next few seconds. And second, which is purely on human demonstrations, human-driven data, giving a score on how close is your given selected action to a human-driven trajectory. The scoring helps us prune the search space, keep branching further on the interactions, and focus the compute on the most promising outcomes. The cool part about this architecture is that it allows us to create a cool blend between data-driven approaches, where you don't have to rely on a lot of hand-engineered costs, but also ground it in reality with physics-based checks. Now, a lot of what I described was with respect to the agents we could observe in the scene, but the same framework extends to objects behind occlusions. We use the video feed from 8 cameras to generate the 3D occupancy of the board. The blue mask here corresponds to the visibility region, we call it. It basically gets blocked at the first occlusion you see in the scene. We consume this visibility mask to generate what we call as ghost objects, which you can see on the top left. Now, if you model the spawn regions and the state transitions of these ghost objects correctly, if you tune your control response as a function of their existence likelihood, you can extract some really nice human-like behaviors. Now, I'll pass it on to Phil to describe more on how we generate these occupancy networks. Thank you.
Hey guys, my name is Phil. I will share the details of the occupancy network we built over the past year. This network is our solution to model the physical world in 3D around our cars. And it is currently not shown in our customer-facing visualization. And what you will see here is the raw network output from our internal dev tool. The occupancy network takes video streams of all our 8 cameras as input, produces a single unified volumetric occupancy in vector space directly. For every 3D location around our car, it predicts the problem.
Una de las cosas que decía hace un rato justamente es si el robot no va a tener algo que prediga lo que está por suceder, nada, va a ser retrucho. Así que justo están hablando de eso, de cómo en el auto hacen para predecir y está muy bueno. La duda es porque aún no está implementado en el robot y es lo que decía la chica del principio. El form factor es distinto, los sensores son distintos y la implementación es desde cero. Así que es mucho trabajo.
Probability of that location being occupied or not. Since it has video context, it is capable of predicting obstacles that are occluded instantaneously. For each location, it also produces a set of semantics such as curb, car.
Lo interesante de esta charla, como dice que es un evento de recruiting, es tratar de entender desde el punto de vista del negocio y de la tecnología que todavía tienen que desarrollar, cuáles son los puestos que van a estar necesitando, qué conocimientos tienen que tener los developers que quieren aplicar y, bueno, eso, qué van a estar desarrollando, qué tamaños van a tener los equipos, en qué países van a estar, si van a ser remotos, todas esas cosas.
Car, pedestrian, and road debris, as color-coded here. occupancy flow is also predicted for motion. Since the model is a generalized network, it does not tell static and dynamic objects explicitly. It is able to produce and model the random motion, such as a swerving trainer here. This network is currently running in all Teslas with FSD computers, and it is incredibly efficient, runs about every 10 milliseconds with our neural net accelerator. So how does this work? Let's take a look at the architecture. First, we rectify each camera images with the camera calibration. And the images we're showing here were given to the network. It's actually not the typical 8-bit RGB image. As you can see from the first image on top, we're giving the 12-bit raw photon count image to the network. Since it has 4 bits more information, it has 16 times better dynamic range, as well as reduced latency, since we don't have to run ISP in the loop anymore. We use a set of reglets and FPNs as a backbone to extract image space features. Next, we construct a set of 3D position query along with the image space features as keys and values fit into an attention module. The output of the attention module is high-dimensional spatial features. These spatial features are aligned temporally using vehicle odometry to derive motion. Last, these spatial temporal features go through a set of deconvolution to produce the final occupancy and occupancy flow output. They're formed as fixed-size voxel grid, which might not be precise enough for planning and control. In order to get a higher resolution, we also produce per voxel feature maps, which we feed into MLP with 3D spatial point queries to get position and semantics at any arbitrary location. After knowing the model better, let's take a look at another example. Here, we have an articulated bus parked on the right side of the road, highlighted as an L-shaped voxel here. As we approach, the bus starts to move. The front of the car turns blue first, indicating the model predicts the front of the bus has a non-zero occupancy flow. And as the bus keeps moving, the entire bus turns blue. And you can also see that the network predicts the precise curvature of the bus. Well, this is a very complicated
Este es el dynamic tagging que mencionaban anteriormente en el otro modelo.
Problem for traditional object detection network, as you have to see whether I'm going to use one cuboid or perhaps 2 to fit the curvature. But for our occupancy network, since all we care about is the occupancy in the visible space, and we'll be able to model the curvature precisely. Besides the voxel grid, the occupancy network also produces a drivable surface. The drivable surface has both 3D geometry and semantics. They are very useful for control, especially on hilly and curvy roads. The surface and the voxel grid are not predicted independently. Instead, the voxel grid actually aligns with the surface implicitly. Here, we're at a hill crest where you can see the 3D geometry of the surface being predicted nicely.
De hecho no. Esto es solamente el modelo predictivo donde solamente muestra lo que piensa que va a pasar. Cuando antes se referían al tagueo automático, es la identificación de objetos. Y siempre siempre me frustra lo mismo de este tipo de modelos de inteligencia artificial, que si bien son súper avanzados y se puede lograr un montón de cosas, es como fuerza bruta de cantidad de datos. No puede intuir que una cosa va a suceder si no la vio antes en algún escenario. Entonces la limitación es solamente hacer cosas que ya alguna vez sucedieron, o una combinación de cosas que hayan sucedido. Es decir, si encuentra un tornillo y encuentra un tornillo de otro tipo, con otras características, no va a entender la implicancia de un tornillo u otro. Si lo tiene tagueado previamente, va a decir que los dos son un tornillo. Ese es en el predictivo. No puede intuir algo que no esté previamente cargado en la base de datos de cosas tagueadas a mano. Y está buenísimo para todo lo que decía antes del movimiento, pero es software nada, es complejo, o sea, que necesita mucho procesamiento. ¿Cómo hacen eso? Muy interesante.
Can use this information to decide perhaps we need to slow down more for the hill crest. And as you can also see, the voxel grid aligns with the surface consistently. Besides the voxels and the surface, we're also very excited about the recent breakthrough in neural radiance field, or NeRF. We're looking into both incorporate some of the nice NeRF features into occupancy network training, as well as using our network output as the input state for NeRF. As a matter of fact, Ashok is very excited about this. This has been his personal weekend project for a while.
About these NeRFs, because I think the academia is building a lot of these foundation models for language, using like tons of large data sets for language. But I think for vision, NeRFs are going to provide the foundation models for computer vision, because they are ground.
O sea, el problema, el dilema inicial de la razón por la cual no me gusta ese approach es porque cada cosa está aislada y separada de lo demás. Es como que no son cosas separadas y cada una es un modelo aparte separado. Y la interacción viene después. Y no sé, es como que hay algo conceptual que está faltando ahí, no tengo muy bien claro qué es, pero hay algo que falta.
In geometry, and geometry gives us a nice way to supervise these networks and frees us of the requirement.
Es decir, si vos diseñas un modelo de inteligencia artificial para navegar un avión y agarrás ese mismo modelo y lo pones en un submarino, no sabe navegar el submarino, porque todas las condiciones del exterior son distintas. Y es exactamente lo mismo que pasa con esto. No pueden agarrar lo que está funcionando en el auto y ponerlo en el form factor del humanoide, porque todo el entorno es distinto, la física misma de cómo se mueve y todo es absolutamente distinto, entonces necesita fuerza bruta de datos. Brum.
To define an ontology, and the supervision is essentially free because you just have to differentially render these images. So I think in the future, this occupancy network idea where images come in and then the network produces a consistent volumetric representation of the scene that can then be differentially rendered into any image that was observed, I personally think is a future of computer vision. And we do some initial work on it right now, but I think in the future, both at Tesla and in the academia, we will see that these combination of one-shot prediction of full volumetric occupancy will be the future. That's my personal bet.
Thanks, Ashok. So here's an example early result of a 3D reconstruction from our fleet data. Instead of focusing on getting perfect RGB reprojection in image space, our primary goal here is to accurately represent the world in 3D space for driving. And we want to do this for all our fleet data all over the world.
Esos modelos son hermosos.
In all weather and lighting conditions.
Quisiera tener la posibilidad de generar uno acá en casa.
We're looking for you guys to help. Finally, the occupancy network is trained with large auto-label dataset without any human in the loop. And with that, I'll pass to Tim to talk about what it takes to train this network.
Poner unas cámaras acá arriba y generar el modelo 3D en tiempo real sería muy bueno.
All right, hey everyone. Let's talk about some training infrastructure. So we've seen a couple of videos, 4 or 5. I think and care more and worry more about a lot more clips than that. So we've been looking at the occupancy networks just from Phil. Just Phil's videos, it takes 1.4 billion frames to train that network, what you just saw. And if you have 100,000 GPUs, it would take 1 hour. But if you have one GPU, it would take 100,000 hours. So that is not a humane time period that you can wait for your training job to run, right? We want to ship faster than that. So that means you're going to need to go parallel. So you need more compute for that. That means you're going to need a supercomputer. So this is why we've built in-house 3 supercomputers comprising of 14,000 GPUs, where we use 10,000 GPUs for training and run 4,000 GPUs for auto-labeling. All these videos are stored in 30 petabytes of a distributed, managed video cache. You shouldn't think of our data sets as fixed, let's say, as you think of your ImageNet or something, with like 1 million frames. you should think of it as a very fluid thing. So we've got 500,000 of these videos flowing in and out of these clusters every single day. And we track 400,000 of these kind of Python video instantiations every second. So that's a lot of calls. We're going to need to capture that in order to govern the retention policies of this distributed video cache. So underlying all of this is a huge amount of infra, all of which we build and manage in-house. So you cannot just buy 14,000 GPUs and then 30 petabytes of flash NVMe and just put it together and let's go train. It actually takes a lot of work, and I'm going to go into a little bit of that. What you actually typically want to do is you want to take your accelerator, so that could be the GPU or Dojo, which we'll talk about later, and because that's the most expensive component, that's where you want to put your bottleneck. And so that means that every single part of your system is going to need to outperform this accelerator. And so that is really complicated. That means that your storage is going to need to have the size and the bandwidth to deliver all the data down into the nodes. These nodes need to have the right amount of CPU and memory capabilities to feed into your machine learning framework. This machine learning framework then needs to hand it off to your GPU, and then you can start training. But then you need to do so across hundreds or thousands of GPU in a reliable way, in lockstep, and in a way that's also fast. So you're also going to need an interconnect. Extremely complicated. We'll talk more about Dojo in a second. So first, I want to take you through some optimizations that we've done on our cluster. So we're getting in a lot of videos, and video is very much unlike, let's say, training on images or text, which I think is very well established. Video is quite literally a dimension more complicated. And so that's why we needed to go end-to-end from the storage layer down to the accelerator and optimize every single piece of that. Because we train on the photon count videos that come directly from our fleet, we train on those directly. We do not post-process those at all. The way it's just done is we seek exactly to the frames we select for our batch. We load those in, including the frames that they depend on. So these are your iframes or your keyframes. We package those up, move them into shared memory, move them into a double buffer on the GPU, and then use the hardware decoder that's only accelerated to actually decode the video. So we do that on the GPU natively. And this is all in a very nice PyTorch extension. Doing so unlocked more than 30% training speed increase for the occupancy networks and freed up basically the whole CPU to do any other thing. You cannot just do training with just videos. Of course, you need some kind of a ground truth. And that is actually an interesting problem as well. The objective for storing your ground truth is that you want to make sure you get to your ground truth that you need in the minimal amount of file system operations and load in the minimal size of what you need in order to optimize for aggregate cross-cluster throughput. Because you should see a compute cluster as one big device which has internally fixed constraints and thresholds. So for this, we rolled out a format that is native to us that's called small. We use this for our ground truth, our feature cache, and any inference outputs. So a lot of tensors that are in there. And so just a cartoon here, let's say these are is your table that you want to store, then that's how that would look out if you rolled out on disk. So what you do is you take anything you'd want to index on, so for example, video timestamps, you put those all in the header, so that in your initial header read, you know exactly where to go on disk. Then if you have any tensors, you're going to try to transpose the dimensions to put a different dimension last as the contiguous dimension, and then also try different types of compression. Then you check out which one was most optimal, and then store that one. This is actually a huge tip if you do feature caching. Unintelligible output from the machine learning network, rotate around the dimensions a little bit, you can get up to 20% increase in efficiency of storage. Then when you store that, we also order the columns by size so that all your small columns and small values are together, so that when you seek for a single value, you're likely to overlap with the read on more values, which you'll use later, so that you don't need to do another file system operation. So I could go on and on. I just went on, touched on 2 projects that we have internally, but this is actually part of a huge continuous effort to optimize the compute that we have in-house. So accumulating and aggregating through all these optimizations, we now train our occupancy networks twice as fast just because it's twice as efficient. And now if we add in a bunch more compute and go parallel, we can now train this in hours instead of days. And with that, I'd like to hand it off to the biggest user of compute, John.
Aprovecho para poner pausa ahí que cortó. Respecto de un modelo no supervisado, y es lo que venía pensando todo el tiempo, es mientras el contexto sea exactamente igual siempre, o sea, agarrás 20 de estos, los pones en una fábrica y que vayan haciendo cosas o aprendiendo cómo se mueve todo y todo, y encima me imagino que en todos los meses siguientes van a mejorar cómo se mueven y van a tener un montón más de información pretagueada. El escenario más difícil que le veo para un modelo sin supervisión es el ambiente hogareño, donde a veces hay más personas de lo habitual, donde todo es muy dinámico. Ahí no lo veo, la verdad que para el mundo real no lo veo, pero para una fábrica sí, 10 puntos.
Hi everybody, my name is John Emmons. I lead the Autopilot Vision team. I'm going to cover two topics with you today. The first is how we predict lanes, and the second is how we predict the future behavior of other agents on the road. In the early days of Autopilot, we modeled the lane detection problem as an image space instance segmentation task. Our network was super simple though. In fact, it was only capable of predicting lanes of a few different kinds of geometries. Specifically, it would segment the eagle lane, it could segment adjacent lanes, and then it had some special casing for forks and merges. This simplistic modeling of the problem worked for highly structured roads like highways. But today we're trying to build a system that's capable of much more complex maneuvers. Specifically, we want to make left and right turns at intersections, where the road topology can be quite a bit more complex and diverse. When we try to apply this simplistic modeling of the problem here, it just totally breaks down. Taking a step back for a moment, what we're trying to do here is to predict the sparse set of lane instances and their connectivity. And what we want to do is to have a neural network that basically predicts this graph, where the nodes are the lane segments, and the edges encode the connectivities between these lanes. So what we have is our lane detection neural network. It's made up of three components. In the first component, we have a set of convolutional layers, attention layers, and other neural network layers that encode the video streams from our 8 cameras on the vehicle and produce a rich visual representation. We then enhance this visual representation with a coarse road-level map data, which we encode with a set of additional neural network layers that we call the lane guidance module. This map is not an HD map, but it provides a lot of useful hints about the topology of lanes inside of intersections, the lane counts on various roads, and a set of other attributes that help us. The first two components here produced a dense tensor that sort of encodes the world. But what we really want to do is to convert this dense tensor into a sparse set of lanes and their connectivities. We approach this problem like an image captioning task, where the input is this dense tensor, and the output text is predicted into a special language that we developed at Tesla for encoding lanes and their connectivities. In this language of lanes, the words and tokens are the lane positions in 3D space. In the ordering of the tokens, and predicted modifiers in the tokens encode the connective relationships between these lanes. By modeling the task as a language problem, we can capitalize on recent autoregressive architectures and techniques from the language community for handling the multimodality of the problem. We're not just solving the computer vision problem at Autopilot, we're also applying the state-of-the-art in language modeling and machine learning more generally. I'm now going to dive into a little bit more detail of this language component. What I have depicted on the screen here is a satellite image which sort of represents the local area around the vehicle. The set of nodes and edges is what we refer to as the lane graph, and it's ultimately what we want to come out of this neural network. We start with a blank slate. We're going to want to make our first prediction here at this green dot. This green dot's position is encoded as an index into a coarse grid which discretizes the 3D world. Now, we don't predict this index directly because it would be too computationally expensive to do so. There's just too many grid points, and predicting a categorical distribution over this has both implications at training time and test time. So instead what we do is we discretize the world coarsely first. We predict a heat map over the possible locations, and then we latch in the most probable location. Condition on this, we then refine the prediction and get the precise point. Now we know where the position of this token is, but we don't know its type. In this case, though, it's the beginning of a new lane. So we predict it as a start token. And because it's a start token, there's no additional attributes in our language. We then take the predictions from this first forward pass, and we encode them using a learned conditional embedding, which produces a set of tensors that we combine together, which is actually the first word in our language of lanes. We add this to the first position in our sentence here. We then continue this process by predicting the next lane point in a similar fashion. Now, this lane point is not the beginning of a new lane. It's actually a continuation of the previous lanes. So it's a continuation token type. Now, it's not enough just to know that.
Esto, como cualquier otro approach, siempre se trata de elegir el contexto en el cual hacer la evaluación o enseñarle al robot a hacer la evaluación. Nunca se trata, ojalá se tratase, mejor dicho, de algo que le enseña a asumir y a inventar el significado de un nuevo contexto. A ese punto todavía no llegamos. Creo que el approach de la misma base de inteligencia en la que se basa esto, si es que comparte algo con OpenAI, ya que Elon Musk está involucrado en ese proyecto también, creo que el approach viene por el lado de la inteligencia artificial ayudando a escribir código. Eso me parece súper válido porque cada bloque de código escrito es una idea nueva, es un concepto nuevo, como de semiología, un nuevo significado, que es un building block para construir cosas más arriba. Esto, nada, es una visión también narrow, no, o sea, es súper útil, no digo que no, pero justamente recién estaba comentando por WhatsApp que lo que asumen en este approach es que van a haber errores, pero que de todas maneras los autos autónomos van a generar menos accidentes que si fueran conductores humanos. O sea, asumen un error y asumen que va a haber una cantidad de muertes y accidentes y de todo, pero menos que con los humanos. Y quizás hasta 99% menos, que es algo que dista de lo ideal. Y conceptualmente tiene como un error filosófico o algo que me molesta, que es eso, como decir, con que sea mejor alcanzar, que estoy de acuerdo, pero dista de lo ideal.
This lane is connected to the previously predicted lane. We want to encode its precise geometry, which we do by regressing a set of spline coefficients. We then take this lane, we encode it again, and add it as the next word in the sentence. We continue predicting these continuation lanes until we get to the end of the prediction grid. We then move on to a different lane segment. So you can see that cyan dot there. Now, it's not topologically connected to that pink point. It's actually forking off of that green point there. So it's got a fork type. And fork tokens actually point back to previous tokens from which the fork originates. So you can see here the fork point predictor is actually the index 0. So it's actually referencing back to tokens that it's already predicted, like you would in language. We continue this process over and over again until we've enumerated all of the tokens in the lane graph. And then the network predicts the end of sentence token.
Yeah, I just want to note that the reason we do this is not just because we want to build something complicated. It almost feels like a Turing-complete machine here with neural networks, though. Is that we tried simpler approaches. For example, trying to just segment the lanes along the road or something like that. But then the problem is when there's uncertainty. Say you cannot see the road clearly, and there could be 2 lanes or 3 lanes, and you can't tell. A simple segmentation-based approach would just draw both of them. It's kind of a 2.5 lane situation. And the post-processing algorithm would hilariously fail when the predictions are such.
Yeah, and the problems don't end there. I mean, you need to predict these connective lanes inside of intersections, which it's just not possible with the approach that Ashok's mentioning, which is why we had to upgrade to this sort of.
Yeah, when it overlaps like this, segmentation would just go haywire. But even if you try very hard to put them on separate layers, it's just a really hard problem. But language just offers a really nice framework for getting a sample from a posterior as opposed to trying to do all of this in post-processing. But this doesn't actually stop for just autopilot, right, John? This can be used for Optimus.
Yeah, I guess they wouldn't be called lanes, but you could imagine, sort of in this, stage here, that you might have sort of paths that sort of, encode the possible places that people could walk.
Yeah, basically, if you're in a factory or in a, home setting, you can just ask the robot, okay, please route to the kitchen, or please route to some location in the factory, and then we predict a set of pathways that would go through the aisles, take the robot, and say, okay, this is how you get to the kitchen. It just really gives us a nice framework to model these different paths that simplify the navigation problem for the downstream planner.
All right, so ultimately what we get from this lane detection network is a set of lanes in their connectivities, which comes directly from the network. There's no additional step here for sparsifying these dense predictions into sparse ones. This is just the direct, unfiltered output of the network. Okay, so I talked a little bit about lanes. I'm going to briefly touch on how we model and predict the future paths and other semantics on objects. So I'm just going to go really quickly through 2 examples. The video on the right here, we've got a car that's actually running a red light and turning in front of us. What we do to handle situations like this is we predict a set of short time horizon future trajectories on all objects. We can use these to anticipate the dangerous situation here and apply whatever braking and steering actions required to avoid a collision. In the video on the right, there's 2 vehicles in front of us. The one in the left lane is parked. Apparently it's being loaded, unloaded. I don't know why the driver decided to park there. But the important thing is that our neural network predicted that it was stopped, which is the red color there. The vehicle in the other lane, as you notice, also is stationary. But that one's obviously just waiting for that red light to turn green. So even though both objects are stationary and have 0 velocity, it's the semantics that is really important here so that we don't get stuck behind that awkwardly parked car. Predicting all of these agent attributes presents some practical problems when trying to build a real-time system. We need to maximize the frame rate of our object detection stack so that autopilot can quickly react to the changing environment. Every millisecond really matters here. To minimize the inference latency, our neural network is split into 2 phases. In the first phase, we identify the locations in 3D space where agents exist. In the second stage, we then pull out tensors at those 3D locations, append it with additional data that's on the vehicle, and then we do the rest of the processing. This sparsification step allows the neural network to focus compute on the areas that matter most, which gives us superior performance for a fraction of the latency cost. So putting it all together, the autopilot vision stack predicts more than just the geometry and kinematics of the world. It also predicts a rich set of semantics, which enables safe and human-like driving. I'm now going to hand things off to Sri, who will tell us how we run all these cool neural networks on our FSD computer. Thank you.
Hi everyone, I'm Sri. Today I'm going to give a glimpse of what it takes to run these FSD networks in the car and how do we optimize for the inference latency. Today I'm going to focus just on the FSD lanes network that John just talked about. So when we started this track, we wanted to know if we can run this FSD lanes network natively on the TRIP engine, which is our in-house neural network accelerator that we built in the FSD computer. When we built this hardware, we kept it simple and we made sure it can do one thing ridiculously fast, dense dot products. But this architecture is auto-regressive and iterative, where it crunches through multiple attention blocks in the inner loop, producing sparse points directly at every step. So the challenge here was, how can we do this sparse point prediction and sparse computation on a dense dot product engine? Let's see how we did this on the TRIP. So the network predicts the heat map of most probable spatial locations of the point. Now we do a argmax and a one-hot operation, which gives the one-hot encoding of the index of the spatial location. Now we need to select the embedding associated with this index from an embedding table that is learned during training. To do this on TRIP, we actually built a lookup table in SRAM, and we engineered the dimensions of this embedding such that we could achieve all of this thing with just matrix multiplication. Not just that, we also wanted to store this embedding.
A ver, tengo en el WhatsApp una discusión acerca de la inteligencia artificial y obviamente no quiero ser como súper crítico porque está buenísimo, pero no creo que sea el approach correcto de inteligencia artificial, pero nada, eso es como para hablarlo en otro contexto. Pero sí el patrón que noto es la diferencia que tiene los autos Tesla con autos de otra empresa respecto de el self-driving, es que ninguna otra empresa tiene tanta información, tantos videos, tantos modelos, tanta información tagueada, aunque sea automáticamente. Ni Cruise, ni Uber, ni ninguna otra empresa tiene tanta información. Fíjense que si es que usa el mismo modelo de OpenAI, cumple exactamente el mismo patrón que la herramienta que te ayuda a escribir código, que es GitHub Copilot. Compraron el repositorio de GitHub, lo pasaron por el modelo de auto-tagging, de identificación de patrones, y eso es lo que tiene poder, la cantidad de datos que tienen procesados por ese modelo. Y con esto va a ser lo mismo respecto de cualquier otro robot o iniciativa que haya habido en el pasado, donde por ahí construían un modelo, 2, 3, lo que decía Elon Musk es: vamos a construir cientos o miles o cientos de miles, y esos van a estar todo el tiempo filmando toda esa cantidad de información tagueada. Ese es el poder que tienen. Por lo tanto, el approach, por más naive que sea, que no lo es, pero por más que lo fuera, el approach de inteligencia artificial con tantos datos, de todas maneras procedería muy bien. Y a partir de ahí, la mejora constante hasta que haya alguna evolución en la tecnología de inteligencia simulada, digamos, porque inteligencia artificial es estadística y tiene un límite, y es este. Es muy bueno, pero no es ideal.
Into a token cache so that we don't recompute this for every iteration, rather reuse it for future point prediction. Again, we pulled some tricks here where we did all these operations just on the dot product engine. It's actually cool that our team found creative ways to map all these operations on the trip engine in ways that were not even imagined when this hardware was designed. But that's not the only thing we had to do to make this work. We actually implemented a whole lot of operations and features to make this model compilable, to improve the intent accuracy, as well as to optimize performance. All of these things helped us run this 75 million parameter model just under 10 milliseconds of latency, consuming just 8 watts of power. But this is not the only architecture running in the car. There are so many other architectures, modules, and networks we need to run in the car. To give a sense of scale, there are about 1 billion parameters of all the networks combined, producing around 1,000 neural network signals. So we need to make sure we optimize them jointly and such that we maximize the compute utilization, throughput, and minimize the latency. So we built a compiler just for neural networks that shares the structure to traditional compilers. As you can see, it takes the massive graph of neural nets with 150K nodes and 375K connection, takes this thing, partitions them into independent subgraphs, and compiles each of those subgraphs natively for the inference devices. Then we have a neural network linker which shares the structure to traditional linker, where we perform this link time optimization. There we solve an offline optimization problem with compute memory and memory bandwidth constraints, so that it comes with an optimized schedule that gets executed in the car. On the runtime, we designed a hybrid scheduling system which basically does heterogeneous scheduling on one SoC and distributed scheduling across both the SoCs to run these networks in a model parallel fashion. To get 100 TOPS of compute utilization, we need to optimize across all the layers of software, right from tuning the network architecture, the compiler, all the way to implementing a low latency, high bandwidth RDMA link across both the SoCs, and in fact, going even deeper to understanding and optimizing the cache coherent and non-coherent data paths of the accelerator in the SoC. This is a lot of optimization at every level in order to make sure we get the highest frame rate, and as every millisecond counts here. And this is just the visualization of the neural networks that are running in the car. This is our digital brain, essentially. As you can see, these operations are nothing but just the matrix multiplication, convolution, to name a few, real operations running in the car. To train this network with 1 billion parameters, you need a lot of labeled data. So Egan is going to talk about how do we achieve this with the auto labeling pipeline.
Thank you, Sri. Hi, everyone. I'm Yegan Zhang, and I'm leading geometric vision and autopilot. So, yeah, let's talk about auto labeling. So we have several kinds of auto labeling frameworks to support various types of networks. But today, I'd like to focus on the awesome LanesNet here. So to successfully train and generalize this network to everywhere, we think we went tens of millions of trips from probably 1 million intersection or even more. So then how to do that? So it is certainly achievable to source sufficient amount of trips because we already have, as Tim explained earlier, we already have like 500,000 trips per day cache rate. However, converting all those data into a training form is a very challenging technical problem. To solve this challenge, we've tried various ways of manual and auto labeling. So from the first column to the second, from the second to the third, each advance provided us nearly 100x improvement in throughput. But still, we run an even better auto labeling machine that can provide us good quality, diversity, and scalability. To meet all these requirements, despite the huge amount of engineering effort required here, we've developed a new auto labeling machine powered by multi-trip reconstruction. So this can replace 5 million hours of manual labeling with just 12 hours on cluster for labeling 10,000 trips. So how is solved? There are 3 big steps. The first step is high precision trajectory and structure recovery by multi-camera, visual inertial odometry. So here, all the features, including ground surface, are inferred from videos by neural networks, then tracked and reconstructed in the vector space. So the typical drift rate of this trajectory in car is like 1.3 centimeter per meter and 0.45 milliradian per meter, which is pretty decent considering its compact compute requirement. Then the recovered surface and road details are also used as a strong guidance for the later manual verification step. This is also enabled in every FSD vehicle, so we get pre-processed trajectories and structures along with the trip data. Auto-labeling the new trips. So here we use the same multi-trip alignment engine, but only between pre-built reconstruction and each new trip. So it's much, much simpler than fully reconstructing all the clips altogether. That's why it only takes 30 minutes per trip to auto-label instead of several hours of manual labeling.
Auto-label our lanes, but we have auto-labelers for almost every task that we do, including our planner. And many of these are fully automatic. There's no humans involved. For example, for objects, all of the kinematics, the shapes, the features, everything just comes from auto-labeling. And the same is true for occupancy too. And we have really just built a machine around this.
Yeah, so if you can go back one slide. One more. It says parallelized on cluster. So that sounds pretty straightforward, but it really wasn't. Maybe it's fun to share how something like this comes about. So a while ago, we didn't have any auto-labeling at all. And then someone makes a script, it starts to work, it starts working better until we reach a volume that's pretty high and we clearly need a solution. And so there were 2 other engineers in our team who were like, hey, that's an interesting thing. What we needed to do was build a whole graph of essentially Python functions that would need to run one after the other. First you pull the clip, then you do some cleaning, then you do some network inference, then another network inference, until you finally get this. So you need to do this at a large scale. So I tell them, we probably need to shoot for 100,000 clips per day, or like 100,000 items. That seems good. And so the engineer said, well, we can do a bit of Postgres and a bit of elbow grease. We can do it. Meanwhile, we are a bit later, and we're doing 20 million of these functions every single day. Again, we pull in around 500,000 clips, and on those, we run a ton of functions, each of these, in a streaming fashion. And so that is kind of the back-end infra that's also needed to not just run training, but also auto-labeling.
Yeah, it really is like a factory that produces labels, and like production lines, yield, quality, inventory, like all of the same concepts apply to this label factory that applies for the factory for our cars.
That's right.
Okay, thanks, Tim and Ashok. So concluding this section, I'd like to share a few more challenging and interesting examples for network for sure, and even for humans probably. So from the top, there's like examples for like lack of light case or foggy night or roundabout and heavy occlusions by parked cars, and even rainy night with the raindrops on camera lenses. These are challenging, but once their original scenes are fully reconstructed by other clips, all of them can be auto-labeled so that our cars can drive even better through these challenging scenarios. So now, let me pass the mic to David to learn more about how Sim is creating the new world on top of these labels. Thank you.
Thank you, Yagen. My name is David, and I'm going to talk about simulation. So simulation plays a critical role in providing data that is difficult to source and/or hard to label. However, 3D scenes are notoriously slow to produce. Take, for example, the simulated scene playing behind me, a complex intersection from Market Street in San Francisco. It would take 2 weeks for artists to complete. And for us, that is painfully slow. However, I'm going to talk...
Que este edificio estaba en construcción hace, no sé, 2 años.
Talk about using Yagen's automated ground truth labels along with some brand new tooling that allows us to procedurally generate this scene and many like it in just 5 minutes. That's an amazing 1,000 times faster than before. So let's dive in to how a scene like this is created. We start by piping the automated ground truth labels into our simulated world creator tooling inside the software Houdini. Starting with road boundary labels, we can generate a solid road mesh and retopologize it with the lane graph labels. This helps inform important road details like crossroad slope and detailed material blending. Next, we can use the line data and sweep geometry across its surface and project it to the road, creating lane paint decals. Next, using median edges, we can spawn island geometry and populate it with randomized foliage. This drastically changes the visibility of the scene. Now, the outside world can be generated through a series of randomized heuristics. Modular building generators create visual obstructions, while randomly placed objects like hydrants can change the color of the curbs, while trees can drop leaves below it, obscuring lines or edges. Next, we can bring in map data to inform positions of things like traffic lights or stop signs.
El modelo es hermoso.
We can trace along its normal
lindísimo.
to collect important information like number of lanes and even get accurate street names on the signs themselves. Next, using lane graph.
Por eso me quedé con cara de fantasma recién, porque digo, faltan los alambres como del tranvía, así, no sé cómo se llama, el trolebús. Pero claro, no me di cuenta que era un modelo 3D.
We can determine lane connectivity and spawn directional road markings on the road and their accompanying road signs. And finally, with lane graph itself, we can determine lane adjacency and other useful metrics to spawn randomized traffic permutations inside our simulator. And again, this is all automatic, no artist in the loop, and happens within minutes. And now this sets us up to do some pretty cool things. Since everything is based on data and heuristics, we can start to fuzz parameters to create visual variations of the single ground truth. It can be as subtle as object placement and random material swapping to more drastic changes like entirely new biomes or locations of environment, like urban, suburban, or rural. This allows us to create infinite targeted permutations for specific ground truths that we need more ground truth for. And all this happens within a click of a button. And we can even take this one step further by altering our ground truth itself. Say John wants his network to pay more attention to directional road markings to better detect an upcoming captive left turn lane. We can start to procedurally alter our lane graph inside the simulator to help create entirely new flows through this intersection to help focus the network's attention to the road markings to create more accurate predictions. And this is a great example of how this tooling allows us to create new data that could never be collected from the real world. And the true power of this tool is in its architecture and how...
Crear nueva data que nunca puede ser obtenida del mundo real es fabricar sus propios modelos para entrenar. Fabricar sus propios modelos para entrenar es súper peligroso.
How we can run all tasks in parallel to infinitely scale.
La más correcta definición de un entorno controlado es inventar tus propios datos para simular. Algo súper practicado en la industria y que no me gusta como práctica ni como filosofía.
So you saw the tile creator tool in action, converting the ground truth labels into their counterparts. Next, we can use our tile extractor tool to divide this data into geohash tiles about 150 meters square in size. We then save out that data into separate geometry and instance files. This gives us a clean source of data that's easy to load and allows us to be rendering engine agnostic for the future. Then, using a tile loader tool, we can summon any number of those cache tiles using a geohash ID. Currently, we're doing about these 5x5 tiles or 3x3, usually centered around fleet hotspots or interesting lane graph locations. And the tile loader also converts these tile sets into U assets for consumption by the Unreal Engine and gives you a finished product from what you saw in the first slide. And this really sets us up for size and scale. And as you can see on the map behind us, we can easily generate most of San Francisco city streets. And this didn't take years or even months of work, but rather 2 weeks by one person.
Me cuesta entender lo que es video y lo que es filmado, es como muy loco.
We can continue to manage and grow all this data using our PDG network inside of the tooling. This allows us to throw compute at it and regenerate all these tile sets overnight. This ensures all environments are of consistent quality and features, which is super important for training, since new ontologies and signals are constantly released. And now, to come full circle, because we generated all these tile sets from ground truth data, they contain all the weird intricacies from the real world, and we can combine that with the procedural, visual, and traffic variety to create limitless targeted data for the network to learn from. And that concludes the sim section. I'll pass it to Kate to talk about how we can use all this data to improve autopilot. Thank you.
Grosso, muy impresionante.
Thanks, David. Hi, everyone. My name is Kate Park, and I'm here to talk about the data engine, which is the process by which we improve our neural networks via data. We're going to show you how we deterministically solve interventions via data and walk you through the life of this particular clip. In this scenario, autopilot is approaching a turn and incorrectly predicts that crossing vehicle as stopped for traffic, and thus a vehicle that we would slow down for. In reality, there's nobody in the car. It's just awkwardly parked. We've built this tooling to identify the mispredictions, correct the label, and categorize this clip into an evaluation set. This particular clip happens to be one of 126 that we've diagnosed as challenging parked cars at turns. Because of this infra, we can curate this evaluation set without any engineering resources custom to this particular challenge case. To actually solve that challenge case requires mining thousands of examples like it, and it's something Tesla can trivially do. We simply use our data sourcing infra, request data, and use the tooling shown previously to correct the labels. By surgically targeting the mispredictions of the current model, we're only adding the most valuable examples to our training set. We surgically fix 13,900 clips, and because those were examples where the current model struggles, we don't even need to change the model architecture. A simple weight update with this new valuable data is enough to solve the challenge case. So you see, we no longer predict that crossing vehicle as stopped, as shown in orange, but parked, as shown in red. In academia, we often see that people keep data constant, but at Tesla, it's very much the opposite. We see time and again that data is one of the best, if not the most deterministic lever to solving these interventions. We just showed you the data engine loop for one challenge case, namely these parked cars at turns. But there are many challenge cases even for one signal of vehicle movement. We apply this data engine loop to every single challenge case we've diagnosed, whether it's buses, curvy roads, stopped vehicles, parking lots. And we don't just add data once, we do this again and again to perfect the semantic. In fact, this year, we updated our vehicle movement signal 5 times, and with every weight update trained on the new data, we push our vehicle movement accuracy up and up. This data engine framework applies to all our signals, whether they're 3D, multicam video, whether the data is human-labeled, auto-labeled, or simulated, whether it's an offline model or an online model. And Tesla is able to do this at scale because of the fleet advantage, the infra that our Eng team has built, and the labeling resources that feed our networks. To train on all this data, we need a massive amount of compute, so I'll hand it off to Pete and Ganesh to talk about the Dojo supercomputing platform. Thank you.
La escala es su leverage, es su poder.
Thanks, everybody. Thanks for hanging in there. We're almost there.
Quisiera saber si hay algo
My
de
name's
esto,
Pete Bannon. I run the...
si algo de su modelo es libre o de código abierto. No lo creo, pero ojalá.
Custom silicon and low voltage teams at Tesla.
And my name is Ganesh Venkat. I run the Dojo program.
Thank you. I'm frequently asked, why is a car company building a supercomputer for training? And this question fundamentally misunderstands the nature of Tesla. At its heart, Tesla is a hardcore technology company. All across the company, people are working hard in science and engineering to advance the fundamental understanding and methods that we have available to build cars, energy solutions, robots, and anything else that we can do to improve the human condition around the world. It's a super exciting thing to be a part of, and it's a privilege to run a very small piece of it in the semiconductor group. Tonight we're going to talk a little bit about Dojo and give you an update on what we've been able to do over the last year. But before we do that, I wanted to give a little bit of background on the initial design that we started a few years ago. When we got started, the goal was to provide a substantial improvement to the training latency for our autopilot team. Some of the largest neural networks they train today run for over a month, which inhibits their ability to rapidly explore alternatives and evaluate them. So, a 30x speed up would be really nice if we could provide it at a cost competitive and energy competitive way. To do that, we wanted to build a chip with a lot of arithmetic units that we could utilize at a very high efficiency. And we spent a lot of time studying whether we could do that using DRAM, various packaging ideas, all of which failed. And in the end, even though it felt like an unnatural act, we decided to reject DRAM as the primary storage medium for this system, and instead focus on SRAM embedded in the chip. SRAM provides, unfortunately, a modest amount of capacity, but extremely high bandwidth and very low latency, and that enables us to achieve high utilization with the arithmetic units. Those choices, that particular choice led to a whole bunch of other choices. For example, if you want to have virtual memory, you need page tables. They take up a lot of space. We didn't have space, so no virtual memory. We also don't have interrupts. The accelerator is a bare bones, raw piece of hardware that's presented to a compiler, and the compiler is responsible for scheduling everything that happens in a deterministic way. So there's no need or even desire for interrupts in the system. We also chose to pursue model parallelism as a training methodology, which is not the typical situation. Most machines today use data parallelism, which consumes additional memory capacity, which we obviously don't have. So all of those choices led us to build a machine that is pretty radically different from what's available today. We also had a whole bunch of other goals. One of the most important ones was no limits. So we wanted to build a compute fabric that would scale in an unbounded way for the most part. I mean, obviously there's physical limits now and then, but pretty much if your model was too big for the computer, you just had to go buy a bigger computer. That's what we were looking for. Today, the way machines are packaged, there's a pretty fixed ratio of, for example, GPUs, CPUs, and DRAM capacity and network capacity. And we really wanted to disaggregate all that so that as models evolved, we could vary the ratios of those various elements and make the system more flexible to meet the needs of the autopilot team.
Yeah, and it's so true, Pete, like no limits philosophy was our guiding star all the way. All of our choices were centered around that. And to the point that we didn't want traditional data center infrastructure to limit our capacity to execute these programs at speed. So sorry about that. That's why we integrated vertically our data center, the entire data center. By doing a vertical integration of the data center, we could extract new levels of efficiency. We could optimize power delivery, cooling, and as well as system management across the whole data center stack, rather than doing box by box and integrating those boxes into data centers. And to do this, we also wanted to integrate early to figure out limits of scale for our software workloads. So we integrated Dojo environment into our autopilot software very early, and we learned a lot of lessons. And today, Bill Chang will go over our hardware update, as well as some of the challenges that we faced along the way. And Rajiv Kurian will give you a glimpse of our compiler technology, as well as go over some of our cool results.
Great. There you go. Thanks, Pete. Thanks, Ganesh. I'll start tonight with a high-level vision of our system that'll help set the stage for the challenges and the problems we're solving, and then also how software will then leverage this for performance. Now, our vision for Dojo is to build a single unified accelerator, a very large one. Software would see a seamless compute plane with globally addressable, very fast memory, and all connected together with uniform, high bandwidth, and low latency. Now, to realize this, we need to use density to achieve performance. Now, we leverage technology to get this density in order to break levels of hierarchy all the way from the chip to the scale-out systems. Now, silicon technology has done this for decades. Chips have followed Moore's law for density and integration to get performance scaling. Now, a key step in realizing that vision was our training tile. Not only can we integrate 25 dies at extremely high bandwidth, but we can scale that to any number of additional tiles by just connecting them together. Now, last year, we showcased our first functional training tile, and at that time, we already had workloads running on it. And since then, the team here has been working hard and diligently to deploy this at scale. Now, we've made amazing progress and had a lot of milestones along the way. And of course, we've had a lot of unexpected challenges. But this is where our fail fast philosophy has allowed us to push our boundaries. Now, pushing density for performance presents all new challenges. One area is power delivery. Here, we need to deliver the power to our compute die, and this directly impacts our top-line compute performance. But we need to do this at unprecedented density. We need to be able to match our die pitch with a power density of almost 1 amp per millimeter squared. And because of this extreme integration, this needs to be a multi-tiered vertical power solution. And because there's a complex heterogeneous material stack-up, we have to carefully manage the material transition, especially CTE. Now, why does the coefficient of thermal expansion matter in this case? CTE is a fundamental material property, and if it's not carefully managed, that stack-up would literally rip itself apart. So we started this effort by working with vendors to develop this power solution. But we realized that we actually had to develop this in-house. Now, to balance schedule and risk, we built quick iterations to support both our system bring-up and software development, and also to find the optimal design and stack-up that would meet our final production goals. And in the end, we were able to reduce CTE over 50%, and meet our performance by 3x over our initial version. Now, needless to say, finding this optimal material stack-up while maximizing performance at density is extremely difficult. Now, we did have unexpected challenges along the way. Here's an example where we pushed the boundaries of integration that led to component failures. This started when we scaled up to larger and longer workloads, and then intermittently, a single site on a tile would fail. Now, they started out as recoverable failures, but as we pushed to much higher and higher power, these would become permanent failures. Now, to understand this failure, you have to understand why and how we build our power modules. Solving density at every level is the cornerstone of actually achieving our system performance. Now, because our XY plane is used for high bandwidth communication, everything else must be stacked vertically. This means all other components other than our die must be integrated into our power modules. Now, that includes our clock and our power supplies and also our system controllers. Now, in this case, the failures were due to losing clock output from our oscillators. And after an extensive debug, we found that the root cause was due to vibrations on the module from piezoelectric effects, our nearby capacitors. Now, singing caps are not a new phenomenon, and in fact, very common in power design. But normally, clock chips are placed in a very quiet area of the board and often not affected by power circuits. But because we needed to achieve this level of integration, these oscillators need to be placed in very close proximity. Now, due to our switching frequency and then the vibration resonance created, it caused out-of-plane vibration on our MEMS oscillator that caused it to crack. Now, the solution to this problem is a multi-pronged approach. We can reduce the vibration by using soft terminal caps. We can update our MEMS part with a lower Q factor for the out-of-plane direction. And we can also update our switching frequency to push the resonance further away from these sensitive bands. Now, in addition to the density at the system level, we've been making a lot of progress at the infrastructure level. We knew that we had to re-examine every aspect of the data center infrastructure in order to support our unprecedented power and cooling density. We brought in a fully custom designed CDU to support Dojo's dense cooling requirements. And the amazing part is we're able to do this at a fraction.
Me imagino nitrógeno líquido fluyendo por ahí para enfriar los procesadores, ¿ok?
Of the cost versus buying off the shelf and modifying it. And since our Dojo cabinet integrates enough power and cooling to match an entire row of standard IT racks, we need to carefully design our cabinet and infrastructure together. And we've already gone through several iterations of this cabinet to optimize this. And earlier this year, we started load testing our power and cooling infrastructure. And we were able to push it over 2 megawatts before we tripped our substation and got a call from the city. Yeah. Now, last year, we introduced only a couple of components of our system, the custom D1 die and the training tile. But we teased the exapod as our end goal. We'll walk through the remaining parts of our system that are required to build out this exapod. Now, the system tray is a key part of realizing our vision of a single accelerator. It enables us to seamlessly connect tiles together, not only within the cabinet, but between cabinets. We can connect these tiles at very tight spacing across the entire accelerator, and this is how we achieve our uniform communication. This is a laminated bus bar that allows us to integrate very high power, mechanical and thermal support, and an extremely dense integration. It's 75 millimeters in height and supports 6 tiles at 135 kilograms. This is the equivalent of 3 to 4 fully loaded high-performance racks. Next, we need to feed data to the training tiles. This is where we've developed the Dojo interface processor. It provides our system with high bandwidth DRAM to stage our training data. And it provides full memory bandwidth to our training tiles using TTP, our custom protocol that we use to communicate across our entire accelerator. It also has high-speed Ethernet that helps us extend this custom protocol over standard Ethernet. And we provide native hardware support for this with little to no software overhead. And lastly, we can connect to it through a standard Gen 4 PCIe interface. Now, we pair 20 of these cards per tray, and that gives us 640 gigabytes of high bandwidth DRAM. And this provides our disaggregated memory layer for our training tiles. These cards are our high bandwidth ingest path, both through PCIe and Ethernet. They also provide a high radix Z connectivity path that allows shortcuts across our large Dojo accelerator. Now, we actually integrate the host directly underneath our system tray. These hosts provide our ingest processing and connect to our interface processors through PCIe. These hosts can provide hardware video decoder support for video-based training. And our user applications land on these hosts so we can provide them with the standard x86 Linux environment. Now, we can put 2 of these assemblies into one cabinet and pair it with redundant power supplies that do direct conversion of 3-phase 480-volt AC power to 52-volt DC power. Now, by focusing on density at every level, we can realize the vision of a single accelerator. Now, starting with the uniform nodes on our custom D1 die, we can connect them together in our fully integrated training tile, and then finally, seamlessly connecting them across cabinet boundaries to form our Dojo accelerator. And altogether, we can house 2 full accelerators in our exapod for a combined 1 exaflop of ML compute. Now, altogether, this amount of technology and integration has only ever been done a couple of times in the history of compute. Next, we'll see how software can leverage this to accelerate their performance.
Thanks, Bill. My name is Rajiv, and I'm going to talk some numbers. So our software stack begins with the PyTorch extension that speaks to our commitment to run standard PyTorch models out of the box. We're going to talk more about our JIT compiler and the ingest pipeline that feeds the hardware with data. Abstractly, performance is TOPS times utilization times accelerator occupancy. We've seen how the hardware provides peak performance. It's the job of the compiler to extract utilization from the hardware while code is running on it. And it's the job of the ingest pipeline to make sure that data can be fed at a throughput high enough for the hardware to not ever starve. So let's talk about why communication-bound models are difficult to scale. But before that, let's look at why ResNet 50-like models are easier to scale. You start off with a single accelerator, run the forward and backward passes, followed by the optimizer. Then to scale this up, you run multiple copies of this on multiple accelerators. And while the gradients produced by the backward pass do need to be reduced, and this introduces some communication, this can be done pipeline with the backward pass. This setup scales fairly well, almost linearly. For models with much larger activations, we run into a problem as soon as we want to run the forward pass. The batch size that fits in a single accelerator is often smaller than the batch norm surface. So to get around this, researchers typically run this setup on multiple accelerators in sync batch norm mode. This introduces latency-bound communication to the critical path of the forward pass, and we already have a communication bottleneck. And while there are ways to get around this, they usually involve tedious manual work best suited for a compiler. And ultimately, there's no skirting around the fact that if your state does not fit in a single accelerator, you can be communication bound. And even with significant efforts from our ML engineers, we see such models don't scale linearly. The Dojo system was built to make such models work at high utilization. The high-density integration was built to not only accelerate the compute-bound portions of a model, but also the latency-bound portions, like a batch norm or the bandwidth-bound portions like a gradient all reduce or a parameter all gather. A slice of the Dojo mesh can be carved out to run any model. The only thing users need to do is to make the slice large enough to fit a bashroom surface for their particular model. After that, the partition presents itself as one large accelerator, freeing the users from having to worry about the internal details of execution. And it's the job of the compiler to maintain this abstraction. Fine-grained synchronization primitives and uniform low latency makes it easy to accelerate all forms of parallelism across integration boundaries. Tensors are usually stored sharded in SRAM and replicated just in time for layers execution. We depend on the high Dojo bandwidth to hide this replication time. Tensor replication and other data transfers are overlapped with compute, and the compiler can also recompute layers when it's profitable to do so. We expect most models to work out of the box. As an example, we took the recently released Stable Diffusion model and got it running on Dojo in minutes. Out of the box, the compiler was able to map it in a model parallel manner on 25 Dojo dies. Here are some pictures of a Cybertruck on Mars generated by Stable Diffusion running on Dojo. Looks like it still has some ways to go before matching the Tesla Design Studio team. So we've talked about how communication bottlenecks can hamper scalability. Perhaps an acid test of a compiler and the underlying hardware is executing a cross-die bashform layer. Like mentioned before, this can be a serial bottleneck. So the communication phase of a bashform begins with nodes computing their local mean and standard deviations, then coordinating to reduce these values, then broadcasting these values back, and then they resume their work in parallel. So what would an ideal bashform look like on 25 Dojo dies? Let's say the previous layer's activations are already split across dies. We would expect the 350 nodes on each die to coordinate and produce die local mean and standard deviation values. Ideally, these would get further reduced with the final value ending somewhere towards the middle of the tile. We would then hope to see a broadcast of this value radiating from the center. Let's see how the compiler actually executes a real bashform operation across 25 dies. The communication trees were extracted from the compiler, and the timing is from a real hardware run. We're about to see 8,750 nodes on 25 dies coordinating to reduce and then broadcast the bashform mean and standard deviation values. Die local reduction, followed by global reduction towards the middle of the tie, then the reduced value broadcast radiating from the middle, accelerated by the hardware's broadcast facility. This operation takes only 5 microseconds on 25 Dojo dies. The same operation takes 150 microseconds on 24 GPUs. This is an orders of magnitude improvement over GPUs.
Es una representación
And while we talked
artística
about
del
an all-reduce
procesamiento,
operation
algo
in the
así.
context of a batch norm, it's important to reiterate that the same advantages apply to all other communication primitives. And these primitives are essential for large-scale training. So how about full model performance? So while we think that the ResNet 50 is not a good representation of real-world Tesla workloads, it is a standard benchmark, so let's start there. We are already able to match the A100 die for die. However, perhaps a hint of Dojo's capabilities is that we're able to hit this number with just a batch of 8 per die. But Dojo was really built to tackle larger, complex models. So when we set out to tackle real-world workloads, we looked at the usage patterns of our current GPU cluster. And 2 models stood out: the auto-labeling networks, a class of offline models that are used to generate ground truth, and the occupancy networks that you heard about. The auto-labeling networks are large models that have high arithmetic intensity, while the occupancy networks can be ingest-bound. We chose these models because together they account for a large chunk of our current GPU cluster usage, and they would challenge the system in different ways. So how do we do on these 2 networks? The results we're about to see were measured on multi-die systems for both the GPU and Dojo, but normalized to per-die numbers. On our auto-labeling network, we're already able to surpass the performance of an A100 with our current hardware running on our older generation VRMs. On our production hardware with our newer VRMs, that translates to doubling the throughput of an A100. And our model showed that with some key compiler optimizations, we could get to more than 3x the performance of an A100. We see even bigger leaps on the occupancy network. Almost 3x with our production hardware, with room for more. So what does that mean for Tesla? With our current level of compiler performance, we could replace the ML compute of 1, 2, 3, 4, 5, and 6 GPU boxes with just a single Dojo tile. And this Dojo tile costs less than one of these GPU boxes.
Whoa.
What it really means is that networks that took more than a month to train now take less than a week. Alas, when we measured things, it did not turn out so well. At the PyTorch level, we did not see our expected performance out of the gate. And this timeline chart shows our problem. The teeny tiny little green bars, that's the compile code running on the accelerator. The row is mostly white space where the hardware is just waiting for data. With our dense ML compute, Dojo hosts effectively have 10x more ML compute than the GPU.
Justamente eso es lo que decía hoy, no sé, otra persona, que no hay un momento en que dos cosas que quieran procesar se estén estorbando. Es como que el procesador está súper relajado y procesa las cosas a medida que vienen.
GPU hosts. The data loaders running on this one host simply couldn't keep up with all that ML hardware.
De esa parte no se entiende mucho, pero porque es toda una representación. No te están explicando en realidad lo que pasa. No sé bien, o sea, me imagino que para poder explicar eso va a ser una charla técnica súper densa y súper larga. Así que lo pusieron un poco como los videos de Apple cuando presentan un producto, que ponen esas curvas que no significan nada.
To solve our data loader scalability issues,
pero básicamente lo que dice es, tienen más poder de procesamiento de lo que necesitan para esos modelos en tiempo real.
We knew we had to get over the limit of this single host. The Tesla Transport Protocol moves data seamlessly across host, tiles, and ingest processors. So we extended the Tesla Transport Protocol to work over Ethernet. We then built the Dojo Network Interface card, the DNIC, to leverage TTP over Ethernet. This allows any host with a DNIC card to be able to DMA to and from other TTP endpoints. So we started with the Dojo mesh, then we added a tier of data loading hosts equipped with the DNIC card. We connected these hosts to the mesh via an Ethernet switch. Now every host in this data loading tier is capable of reaching all TTP endpoints in the Dojo mesh via hardware accelerated DMA. After these optimizations went in, our occupancy went from 4% to 97%. So the data loading sections have reduced. The data loading sections have reduced drastically, and the ML hardware is kept busy. We actually expect this number to go to 100% pretty soon. After these changes went in, we saw the full expected speed up from the PyTorch layer, and we were back in business. So we started with hardware design that breaks through traditional integration boundaries in service of our vision of a single giant accelerator. We've seen how the compiler and ingest layers build on top of that hardware. So after proving our performance on these complex real-world networks, we knew what our first large-scale deployment would target: our high arithmetic intensity auto-labeling networks. Today, that occupies 4,000 GPUs over 72 GPU racks. With our dense compute and our high performance, we expect to provide the same throughput with just 4 Dojo cabinets. And these 4 Dojo cabinets will be part of our first exapod that we plan to build by Q1 of 2023. This will more than double Tesla's auto-labeling capacity. The first exapod is part of a total of 7 exapods that we plan to build in Palo Alto right here across the wall. And we have a display cabinet from one of these exapods for everyone to look at.
Es una heladera,
6 tiles densely packed on a tray, 54 petaflops of compute, 640 gigabytes of high bandwidth memory with power and host to feed it. A lot of compute.
A lot of compute.
And we're building out new versions of all our cluster components and constantly improving our software to hit new limits of scale. We believe that we can get another 10x improvement with our next generation hardware. And to realize our ambitious goals, we need the best software and hardware engineers. So please come talk to us or visit tesla.com/AI. Thank you.
Ok, tesla.com/AI. Vamos a entrar y a explorar.
Let me know what
All right, so we, hopefully that was enough detail. And now we can move to questions. Guys, like I think the team come out on stage, and but we really wanted to show the depth and breadth of Tesla in artificial intelligence, compute hardware, robotics actuators, and try to really shift the perception of the company away from, a lot of people think we're like just a car company or we make cool cars, whatever, but they don't have, most people have no idea that Tesla is arguably the leader in real-world AI hardware and software, and that we're building what is arguably the first, the most radical computer architecture since the Cray 1 supercomputer. And I think if you're interested in developing some of the most advanced technology in the world that's going to really affect the world in a positive way, Tesla's the place to be. So yeah, let's fire away with some questions. I think there's a mic at the front and a mic at the back. Or
on this side.
Just throw mics at people. Jump all for the mic.
Yeah, hi, thank you very much. I was impressed here. Yeah. I was impressed very much by Optimus, but I wonder why tendon-driven, the hand? Why did you choose a tendon-driven approach for the hand? Because tendons are not very durable. And why spring-loaded?
Yeah. Hello, is this working? Cool, awesome. Yes, that's a great question. When it comes to any type of actuation scheme, there's trade-offs between, whether or not it's a tendon-driven system or some type of linkage-based system.
Just keep the mic close to your mouth.
A little bit closer?
Yeah.
Hear me? Cool.
Yeah.
The main reason why we went for a tendon-based system is that, first we actually investigated some synthetic tendons, but we found that metallic Bowden cables are, a lot stronger. One of the advantages of these cables is that it's very good for part reduction. We do want to make a lot of these hands, so having a bunch of parts, a bunch of small linkages ends up being a problem when you're making a lot of something. One of the big reasons that tendons are better than linkages in a sense is that you can be anti-backlash. So anti-backlash essentially, allows you to not have any gaps or, stuttery motion in your fingers. Spring-loaded, mainly what spring-loaded allows us to do is allows us to have active opening. So instead of having to have two actuators to drive the fingers closed and then open, we have the ability to, have the tendon drive them closed and then the springs passively extend. And this is something that's seen in our hands as well, right? We have the ability to actively flex, and then we also have the ability to extend. Yeah.
I mean, our goal with Optimus is to have a robot that is maximally useful as quickly as possible. So there's a lot of ways to solve the various problems of a humanoid robot. We're probably not barking up the right tree on all the technical solutions. And I should say that we're open to evolving the technical solutions that you see here over time. They're not locked in stone. But we have to pick something, and we want to pick something that's going to allow us to produce the robot as quickly as possible and have it, like I said, be useful as quickly as possible. We're trying to follow the goal of fastest path to a useful robot that can be made at volume. And we're going to test the robot internally at Tesla in our factory and just see, like, how useful is it? Because you have to have you got to close the loop on reality to confirm that the robot is in fact useful. Yeah, so we're just gonna use it to build things. And we're confident we can do that with the hand that we have currently designed, but for sure there'll be hand version 2, version 3, and we may change the architecture quite significantly over time. Close the loop on reality.
Hi. The Optimus robot is really impressive. You did a great job. Bipedal robots are really difficult. But what I noticed might be missing from your plan is to acknowledge the utility of the human spirit, and I'm wondering if Optimus will ever get a personality and be able to laugh at our jokes while it folds our clothes.
Yeah, absolutely. I think we want to have really fun versions of Optimus, so that Optimus can both be utilitarian and do tasks, but can also be kind of like a friend and a buddy and hang out with you. And I'm sure people will think of all sorts of creative uses for this robot. The thing, once you have the core intelligence and actuators figured out, then you can actually, put all sorts of costumes, I guess, on the robot. I mean, you can make the robot look. You can skin the robot in many different ways, I'm sure people will find very interesting ways to versions of Optimus. So.
Thanks for the great presentation. I wanted to know if there was an equivalent to interventions in Optimus. It seems like labeling through moments where humans disagree with what's going on is important, and in a...
No sé si este es el evento para ese tipo de preguntas. Están bien las preguntas, pero no es para eso esto.
Humanoid robot, that might be also a desirable source of information.
Esa pregunta de reportero no es una pregunta de programador que quiere entrar en el equipo.
We'll have ways to remote operate the robot and intervene when it does something bad,
especially
when we are training the robot and bringing it up. And hopefully we design it in a way that we can stop the robot from, if it's going to hit something, we can just like hold it and then it'll stop. It won't crush your hand or something. And those are all intervention data. And we can learn a lot from our simulation systems too, where we can check for collisions and supervise that those are bad actions.
So Optimus, we want over time for it to be, an android, the kind of android that you've seen in sci-fi movies, like Star Trek, The Next Generation, like Data. But obviously we could program the robot to be less robot-like and more friendly, and it can obviously learn to emulate humans and feel very natural. So as AI in general improves, we can add that to the robot, and it should be obviously able to do simple instructions or even intuit what it is that you want. So you could give it a high-level instruction, and then it can break that down into a series of actions and take those actions.
Hi. It's exciting to think that with the Optimus, you will think that you can achieve orders of magnitude of improvement in economic output. That's really exciting. And when Tesla started, the mission was to accelerate the advent of renewable energy or sustainable transport. So with the Optimus, do you still see that mission being the mission statement of Tesla, or is it going to be updated with, mission to accelerate the advent of, infinite abundance or limitless economy?
It is not, strictly speaking, Optimus is not strictly speaking directly in line with accelerating sustainable energy. To the degree that it is more efficient at getting things done than a person, it does, I guess, help with sustainable energy. But I think the mission effectively does somewhat broaden with the advent of Optimus to, I don't know, making the future awesome. So, I think you look at Optimus, and I don't know about you, but I'm excited to see what Optimus will become. And, this is like, if you could, you can tell, like any given technology, do you want to see what it's like in a year, 2 years, 3 years, 4 years, 5 years, 10? I'd say for sure. You definitely want to see what's happening with Optimus. Whereas, a bunch of other technologies are, sort of plateaued. Won't name names here, but so I think Optimus is going to be incredible in like 5 years, 10 years, like mind-blowing. And I'm really interested to see that happen, and I hope you are too.
Mirá cómo se le dio vuelta a la pregunta.
I have a quick question here.
Muy bien
I'm Justin, and I was wondering, are you planning to extend conversational capabilities for the robot? And my second follow-up question to that is, what's the end goal? What's the end goal with Optimus?
Llegar a Marte.
Yeah, Optimus would definitely have conversational capabilities. You'd be able to talk to it and have a conversation, and it would feel quite natural. So, from an end goal standpoint, I don't know. I think it's going to keep evolving, and I'm not sure where it ends up, but someplace interesting for sure. We always have to be careful about don't go down the Terminator path. That's I thought maybe we should start off with a video of the Terminator starting off with the skull crushing, but that might be people might take that too seriously. So we do want Optimus to be safe, so we are designing in safeguards where you can locally stop the robot, and with basically a localized control ROM that you can't update over the internet, which I think that's quite important, essential, frankly. So like a localized stop button, remote control, something like that cannot be changed. But it's definitely going to be interesting. It won't be boring.
¿Dónde está la palanca para apagarlo el robot? Que la muestren.
Okay, yeah. I see today you have very attractive product with Dojo and its applications. So I'm wondering what's the future for the Dojo platform? Will you provide infrastructure as service like AWS, or you will sell the chip like the NVIDIA? So basically, what's the future? Because I see you use 7 nanometers, so the development cost is easily over $10 million US dollars. How do you make the business business-wise?
Yeah, Dojo is a very big computer, and actually will use a lot of power and needs a lot of cooling. So I think it's probably going to make more sense to have Dojo operate in a Amazon Web Services manner than to try to sell it to someone else. So that would be the most efficient way to operate Dojo, is just have it be a service that you can use that's available online, and that where you can train your models way faster and for less money. And as the world transitions to software 2.0,
and that's on the bingo card.
As someone I know has to now drink 5 tequilas. So let's see. Software 2.0 will use a lot of neural net training. So it kind of makes sense that over time, as there's more neural net stuff, people will want to use the fastest, lowest cost neural net training system. So I think there's a lot of opportunity in that direction.
Hi, my name is Ali Jahanian. Thank you for this event. It's very inspirational. My question is, I'm wondering, what is your vision for humanoid robots that understand our emotions and art and can contribute to our creativity?
Well, I think you're already seeing robots that at least are able to generate very interesting art with like DALL-E and DALL-E 2. And I think we'll start seeing
eso no es arte.
AI that
son
can actually generate
dibujos,
even movies
no es arte.
that have coherence, like interesting movies and tell jokes. So it's quite remarkable how fast AI is advancing at many companies besides Tesla. We're headed for a very interesting future. And yeah, so you guys want to comment on that?
Yeah, I guess the Optimus robot can come up with physical art, not just digital art. You can ask for some dance moves in text or voice, and then you can produce those in the future. So it's a lot of physical art, not just digital art.
Oh, yeah, computers can absolutely make physical art. Yeah, 100%.
Yeah, like dance, play soccer, or whatever you. I mean, it needs to get more agile, but over time.
A ver, un artista que hace una obra de arte puede esconder un significado en una época de prohibición, por ejemplo, y hacer un cuadro que signifique una crítica contra un gobierno. Eso es arte. Cualquier otra cosa es solamente un dibujo.
For sure.
Thanks so much for the presentation. For the Tesla Autopilot slides, I noticed that the models that you were using were heavily motivated by language models. And I was wondering what the history of that was and how much of an improvement it gave. I thought that was a really interesting, curious choice to use language models for the lane transitioning.
So there's sort of two aspects for why we transitioned to language modeling. So the first...
Talk loud and close.
Okay.
It's not coming through very clearly.
Okay, got it. Yeah, so the language models help us in two ways. The first way is that it lets us predict lanes that we couldn't have otherwise. As Ashok mentioned earlier, basically when we predicted lanes in sort of a dense 3D fashion, you can only model certain kinds of lanes, but we want to get those crisscrossing connections inside of intersections. It's just not possible to do that without making it a graph prediction. If you try to do this with dense segmentation, it just doesn't work. Also, the lane prediction is a multimodal problem. Sometimes you just don't have sufficient visual information to know precisely how things look on the other side of the intersection. So you need a method that can generalize and produce coherent predictions. You don't want to be predicting 2 lanes and 3 lanes at the same time. You want to commit to one, and a generative model like these language models provides that.
Hi. My name is Giovanni. Thanks for the presentation. It's really nice. I have a question for FSD team. So for the neural networks, how do you test, how do you do unit tests, software unit tests on that? Like, do you have like a bunch, or I don't know, maybe thousands or cases where the neural network that after you train it, you have to pass it before you release it as a product, right? What's your software unit testing strategies for this, basically?
Yeah, glad you asked. There's like a series of tests that we have defined, starting from unit tests for the software itself, but then for the neural network models, we have VIP sets defined where you can define. If you just have a large test set, that's not enough. What we find, we need like sophisticated VIP sets for different failure modes, and then we curate them and grow them over the time of the product. So over the years, we have like hundreds of thousands of examples where we have been failing in the past that we have curated. And so for any new model, we test against the entire history of these failures and then keep adding to this test set. On top of this, we have shadow modes where we ship these models in silent to the car and we get data back on where they are failing or succeeding. And there's an extensive QA program. It's very hard to ship a regression. There's like 9 levels of filters before it hits customers, but then we have really good infra to make this all efficient.
And I'm one of the QA testers, so I QA the car.
Yeah,
like
QA tester.
Yeah, so I'm constantly in the car just being QAing like whatever the latest alpha build is that doesn't totally crash.
Finds a lot of bugs.
Yeah.
Hi, great event. I have a question about foundational models for autonomous driving. We have all seen that big models that really can, when you scale up with data and model parameter, right, from GPT-3 to PaLM, it can actually now do reasoning. Do you see that is essential scaling up foundational models with data and size, and then at least you can get a teacher model, right, that potentially can solve all the problems, and then you distill to a student model. Is that how you see foundational models relevant for autonomous driving?
That's quite similar to our auto labeling model. So we don't just have models that run in the car. We train models that are entirely offline, that are like extremely large, that can't run in real time on the car. So we just run those offline on the servers, producing really good labels that can then train the online networks. So that's one form of distillation of these teacher-student models. In terms of foundation models, we are building some really, really large data sets that are multiple petabytes. And we are seeing that some of these tasks work really well when we have these large data sets. Like the kinematics, like I mentioned, video in, all the kinematics out of all the objects, and up to the 4th derivative. And people thought we couldn't do detection with cameras. Detection, depth, velocity, acceleration. And imagine how precise these have to be for these higher order derivatives to be accurate. And this all comes from these kind of large data sets and large models. So we're seeing the equivalent of foundation models in our own way for geometry and kinematics and things like those. You want to add anything, John?
Yeah, I'll keep it brief. Basically, whenever we train on a larger data set, we see Basically, whenever we train on a larger data set, we see big improvements in our model performance. And basically, whenever we initialize our networks with some pre-training step from some other auxiliary task, we basically see improvements. The self-supervised or supervised with large data sets both help a lot.
Hi. So at the beginning, Elon said that Tesla was potentially interested in building artificial general intelligence systems. Given the potentially transformative impact of technology like that, it seems prudent to invest in technical AGI safety expertise specifically. I know Tesla does a lot of technical narrow AI safety research. I was curious if Tesla was intending to try to build expertise in technical artificial general intelligence safety specifically.
Well, if it starts looking like we're going to be making a significant contribution to artificial general intelligence, then we'll for sure invest in safety. I'm a big believer in AI safety. I think there should be an AI sort of regulatory authority at the government level, just as there is a regulatory authority for anything that affects public safety. So we have a regulatory authority for aircraft and cars and sort of food and drugs. And because they affect public safety, and AI also affects public safety. So I think, and this is not really something that government, I think, understands yet, but I think there should be a referee that is ensuring or trying to ensure public safety for AGI. And you think of what are the elements that are necessary to create AGI? The accessible data set is extremely important. And if you've got a large number of cars and humanoid robots processing petabytes of video data and audio data from the real world, just like humans, that might be the biggest data set. It probably is the biggest data set. Because in addition to that, you can obviously incrementally scan the internet. But what the internet can't quite do is have millions or hundreds of millions of cameras in the real world, and with like I said, with audio and other sensors as well. So I think we probably will have the most amount of data, and probably the most amount of training power. Therefore, probably we will make a contribution to AGI.
Hey, I noticed the semi was back there, but we haven't talked about it too much. I was just wondering, for the semi-truck, what are the changes you're thinking about from a sensing perspective? I imagine there's very different requirements, obviously, than just a car. And if you don't think that's true, why is that true?
No, I think basically you can drive a car. I mean, think about what drives any vehicle. It's a biological neural net with eyes, with cameras, essentially. So if and really, what is your primary sensors are two cameras on a slow gimbal, a very slow gimbal. That's your head. So if you know, if a biological neural net with two cameras on a slow gimbal can drive a semi-truck, then if you've got like 8 cameras with continuous 360-degree vision, operating at a higher frame rate and much higher reaction rate, then I think it is obvious that you should be able to drive a semi or any vehicle much better than a human.
Hi, my name is Akshay. Thank you for the event. Assuming Optimus would be used for different use cases and would evolve at different pace for these use cases, would it be possible to sort of develop and deploy different software and hardware components independently and deploy them, in Optimus, so that the overall, feature development is faster for Optimus?
Okay, all right. We did not comprehend. Unfortunately, our neural net did not comprehend the question. Yeah, so, well, next question.
Hi, I want to switch the gear to the autopilot. So, when you guys plan to roll out the FSD beta to countries other than US and Canada? And also my next question is, what's the biggest bottleneck or the technological barrier you think in the current autopilot stack? And how you envision to solve that to make the autopilot is considerably better than human in terms of like performance matrix like safety assurance and the human confidence? And I think you also mentioned for FSD V11, you guys going to combine the highway and the city as a single stack and some architectural big improvement. Can you maybe expand a bit on that? Thank you.
Well, that's a whole bunch of questions. Well, we're hopeful to be able to, I think from a technical standpoint, FSD beta should be possible to roll out FSD beta worldwide by the end of this year. But for a lot of countries, we need regulatory approval, and so we are somewhat gated by the regulatory approval in other countries. But I think from a technical standpoint, it will be ready to go to a worldwide beta by the end of this year. And there's quite a big improvement that we're expecting to release next month. That will be especially good at assessing the velocity of fast-moving cross traffic and a bunch of other things. So, anyone want to elaborate?
Yeah, I guess so. There used to be a lot of differences between production autopilot and the full self-driving beta, but those differences have been getting smaller and smaller over time. I think just a few months ago, we now use the same vision-only object detection stack in both FSD and in the production autopilot on all vehicles. There's still a few differences, the primary one being the way that we predict lanes right now. So we upgraded the modeling of lanes so that it could handle these more complex geometries like I mentioned in the talk. In production autopilot, we still use a simpler lane model, but we're extending our current FSD beta models to work in all sort of highway scenarios as well.
Yeah, and the version of FSD beta that I drive actually does have the integrated stack. So,
a ver si el FSD beta o production release puede entender el semáforo de acá a la esquina que está colgando así. A ver si lo entiende. Con la luz roja que no prende muy bien.
Make sure it's working better than the production stack across a wide range of environments. But we're pretty close to that. I mean, I think it's, I don't know, maybe it'll definitely be before the end of the year, and maybe November.
Yeah, in our personal drives, the FSD stack on highway drives already way better than the production stack we have. And we do expect to also include the parking lot stack as a part of the FSD stack before the end of this year. So that will basically bring us to you sit in the car in the parking lot and drive till the end of the parking lot at a parking spot before the end of this year.
Yeah, and in terms of the fundamental metric to optimize gains is how many miles between a necessary intervention. So just massively improving how many miles the car can drive in full autonomy before an intervention is required that is safety critical.
Vos estás muteado.
So, yeah, that's the fundamental metric that we're measuring every week, and we're making radical improvements on that.
Oh, hi. Thank you. Hi. Thank you so much for the presentation. Very inspiring. My name is Daisy. I actually have a non-technical question for you. I'm curious, if you were back to your 20s, what are some of the things you wish you knew back then? What are some advice you would give to your younger self?
Tiene cara de cansado, Elon.
Well, I'm trying to figure out something useful to say. Join Tesla would be one thing. I think just try to expose yourself to as many smart people as possible. I don't know, read a lot of books. I did do that though. I think there's some merit to just also not being necessarily too intense and enjoying the moment a bit more. I would say to 20 or 20-something me, just stop and smell the roses occasionally would probably be a good idea. It's like when we were developing the Falcon 1 rocket and on the Kwajalein Atoll, and we had this beautiful little island that we're developing the rocket on, and not once during that entire time did I even have a drink on the beach. I'm like, well, I should have had a drink on the beach. That would have been fine.
¿Qué rayos está hablando?
Thank you very much. I think you have excited all of the robotics people with Optimus. This feels very much like 10 years ago in driving, but as driving has proved to be harder than it actually looked 10 years ago, what do we know now that we didn't 10 years ago that would make, for example, AGI on a humanoid come faster?
Well, I mean, it seems to me that AGI is advancing very quickly. Hardly a week goes by without some significant announcement. And I mean, at this point, AI seems to be able to win at almost any rule-based game. It's able to create extremely impressive art, engage in conversations that are very sophisticated, write essays, and these just keep improving. And there's so much more, so many more talented people working on AI, and the hardware is getting better. I think AI is on a a strong exponential curve of improvement, independent of what we do at Tesla. And obviously we'll benefit somewhat from that exponential curve of improvement with AI. Tesla just also happens to be very good at actuators, at motors, motors, gearboxes, controllers, power electronics, batteries, sensors, and really, I'd say that the biggest difference between the robot on 4 wheels and the robot with arms and legs is getting the actuators right. It's an actuators and sensors problem. And obviously, how you control those actuators and sensors, but it's actuators and sensors and how you control the actuators. It's I don't know. We have to have the ingredients necessary to create a compelling robot, and we're doing it. So.
Hi, Elon. You are actually bringing the humanity to the next level. Literally, Tesla and you are bringing the humanity to the next level. So you said Optimus Prime, Optimus will be used in next Tesla factory. My question is, will a new Tesla factory will be fully run by Optimus program?
Optimus Prime le mandó.
And when can general public order a humanoid?
Yeah, I think it'll, you know, we're going to start Optimus with very simple tasks in the factory. You know, like maybe just like loading a part, like you saw in the video, loading a part, you know, carrying a part from one place to another, or loading a part into one of our more conventional robot cells to, you know, that welds a body together. So we'll start, you know, just trying to, how do we make it useful at all? And then gradually expand the number of situations where it's useful. And I think that the number of situations where Optimus is useful will grow exponentially, like really, really fast. In terms of when people can order one, I don't know, I think it's not that far away. Well, I think you mean when can people receive one? So, I don't know, I'd say probably within 3 years, and not more than 5 years. Within 3 to 5 years, you could probably receive an Optimus.
I feel the best way to make the progress for AGI is to involve as many smart people across the world as possible. And given the size and resource of Tesla compared to robot companies, and given the state of humanoid research at the moment, would it make sense for the kind of Tesla to sort of open source some of the simulation hardware parts? I think Tesla can still be the dominant platformer where it can be something like Android OS or like iOS stuff for the entire humanoid research. Would that be something that, rather than keeping the Optimus to just Tesla researchers or the factory itself, can you open it and let the whole world explore humanoid research?
Muy buena pregunta, ¿eh? ¿Se hace open source o no?
I think we have to be careful about Optimus being potentially used in ways that are bad, because that is one of the possible things to do. So, I think we'd provide Optimus.
No lo veo posible.
Where you can provide instructions to Optimus, but where those instructions are, governed by some laws of robotics that you cannot overcome. So, not doing harm to others, and you would have, I think, probably quite a few safety-related things with Optimus.
Eso es como no vender cuchillos para que la gente.
All right, we'll just take maybe a few more questions, and then thank you all for coming.
Questions, one deep and one broad. On the deep, for Optimus, what's the current and what's the ideal controller bandwidth? And then in the broader question, there's this big advertisement for the depth and breadth of the company. What is it uniquely about Tesla that enables that?
Anyone want to tackle the bandwidth question?
Yeah. So the technical bandwidth of the...
Close to your mouth and loud.
Okay. For the bandwidth question, you have to understand or figure out what is the task that you want it to do, and what is if you took a frequency transform of that task, what is it that you want your limbs to do? And that's where you get your bandwidth from. It's not a number that you can specifically just say. You need to understand your use case, and that's where the bandwidth comes from. What was the broad question? I don't quite remember.
The breadth and depth thing. I can answer the breadth and depth, but yeah. I mean, it's interesting. On the bandwidth question, I think we probably will just end up increasing the bandwidth, or which translates to the effective dexterity and reaction time of the robot. It's safe to say it's not 1 hertz, and it's maybe you don't need to go all the way to 100 hertz, but I don't know, maybe 10, 25, I don't know. Over time, I think the bandwidth will increase quite a bit, or translated to dexterity and latency. You'd want to minimize that over time. Yeah. minimize latency, maximize dexterity. In terms of breadth and depth, I guess we're a pretty big company at this point, so we've got a lot of different areas of expertise that we necessarily had to develop in order to make autonomous, or in order to make electric cars, and then in order to make autonomous electric cars. Tesla is like a whole series of startups, basically. And so far they've almost all been quite successful. So we must be doing something right. I consider one of my core responsibilities in running the company is to have an environment where great engineers can flourish. And I think in a lot of companies, I don't know, maybe most companies, if somebody's a really talented, driven engineer, they're unable to actually, their talents are suppressed at a lot of companies. And it's, and some of the companies, the engineering talent is suppressed in a way that is maybe not obviously bad, but where it's just so comfortable, and you're paid so much money, and the output you actually have to produce is so low that it's like a honey trap, So like there's a few honey trap places in Silicon Valley where they're not necessarily, don't seem like bad places for engineers, but you have to say like a good engineer went in, and what did they get out? And the output of that engineering talent seems very low, even though they seem to be enjoying themselves. That's why I call it, there's a few honey trap companies in Silicon Valley. Tesla is not a honey trap. We're demanding.
Honey trap sería, por ejemplo, trabajar para Twitter, que
and it's going to be really cool.
Trabajar para una empresa que hace ads.
But if you are a super talented engineer, your talents will be used, I think, to a greater degree than anywhere else. SpaceX also that way. So.
Hi, Ilan. I have two questions. So both to the Autopilot team. So the thing is like, I have been following your progress for the past few years. So today you have made changes on like the lane detection. Like you said that like previously you were doing instant semantic segmentation. Now you guys have built transform models for like building the lanes. So what are some other common challenges which you guys are facing right now, like which you are solving in future as a curious engineer, so that like we as a researcher can work on those, start working on those? And the second question is like, I'm really curious about the data engine. Like you guys have like told a case like where the car is stopped. So how are you finding cases which is very much similar to that from the data which you have? Like, so little bit more on the data engine would be great. So that's it.
Okay. I will answer the first question using the occupancy network as an example. So what you saw in the presentation did not exist a year ago. So we only spent 1 year amount of time. We actually shipped more than 12 occupancy network. And to have one foundation model actually to represent the entire physical world around everywhere and in all weather conditions is actually really, really challenging. So only over a year ago, we're kind of like driving a 2D world. If there's a wall and if there's a curve, we kind of represent with the same static edge, which is obviously, not ideal, right? There's a big difference between a curve and a wall. When you drive, you make different choices, right? So after we realized that we have to go to 3D, we have to basically rethink the entire problem and think about how we address that. So this will be like one example of challenges we have conquered in the past year.
Yeah, to answer the question about how we actually source examples of the tricky stopped cars, there's a few ways to go about this, but two examples are, one, we can trigger for disagreements within our signals. So let's say that parked bit flickers between parked and driving, we'll trigger that back. And the second is we can leverage more of the shadow mode logic. So if the customer ignores the car, but we think we should stop for it, we'll get that data back too. So these are just different, like various trigger logic that allows us to get those data campaigns back.
Hi.
Sorry, go ahead.
Thank you for the amazing presentation. Thanks so much. So there are a lot of companies that are focusing on the AGI problem. And one of the reasons why it's such a hard problem is because the problem itself is so hard to define. Several companies have several different definitions. They focus on different things. So how is Tesla defining the AGI problem, and what are you focusing on specifically?
Well, we're not actually specifically focused on AGI. I'm simply saying that AGI seems likely to be an emergent property of what we're doing. Because we're creating all these autonomous cars and autonomous humanoids that are actually with a truly gigantic data stream that's coming in and being processed. It's by far the most amount of real-world data, and data you can't get by just searching the internet, because you have to be out there in the world and interacting with people and interacting with the roads and just, Earth is a big place. And reality is messy and complicated. So I think it's sort of like it just seems likely to be an emergent property of if you've got, tens or hundreds of millions of autonomous vehicles and maybe even a comparable number of humanoids, maybe more than that on the humanoid front. Well, that's just the most amount of data. And if that video is being processed, it just seems likely that, the cars will definitely get way better than human drivers, and the humanoid robots will become increasingly indistinguishable from humans, perhaps. And so then, like I said, you have this emergent property of AGI. And arguably, humans collectively are sort of a superintelligence as well, especially as we improve the data rate between humans. I mean, the thing that seemed to me way back in the early days of the internet was the internet was like humanity acquiring a nervous system, where now all of a sudden any one element of humanity could know all of the knowledge of humans by connecting to the internet, almost all the knowledge, or certainly a huge part of it. Whereas previously, we would exchange information by osmosis. We'd have to, in order to transfer data, so you would have to write a letter. Someone would have to carry the letter by person to another person, and then a whole bunch of things in between. And then it was insanely slow when you think about it. And even if you were in the Library of Congress, you still didn't have access to all the world's information, and you certainly couldn't search it. And obviously very few people are in the Library of Congress. So, one of the great sort of equality elements, the internet has been the biggest equalizer in history in terms of access to information and knowledge. And any student of history, I think, would agree with this, because you go back 1,000 years, there were very few books. And books would be incredibly expensive, and only a few people knew how to read, and only an even smaller number of people even had a book. Now look at it, you can access any book instantly. You can learn anything basically for free. It's pretty incredible. So, I was asked recently, what period of history would I prefer to be at the most? And my answer was right now. This is the most interesting time in history, and I read a lot of history. So let's do our best to keep that going. Yeah. And to go back to one of the earlier questions I would answer, the thing that's happened over time with respect to Tesla Autopilot is that the neural nets have gradually absorbed more and more software. And in the limit, of course, you could simply take the videos as seen by the car and compare those to the steering inputs from the steering wheel and pedals, which are very simple inputs. In principle, you could train with nothing in between, because that's what humans are doing with a biological neural net. You could train based on video and what trains the video is the moving of the steering wheel and the pedals, with no other software in between. We're not there yet, but it's gradually going in that direction. All right, well, maybe one last question.
How are you going?
I think we've got a question at the front here. Hello, there, right there. We'll do 2 questions, fine.
2 questions, okay. 2 preguntas.
Hi, thanks for such a great presentation.
We'll do your question last.
Okay, cool. With FSD being used by so many people, do you think, how do you evaluate the company's risk tolerance in terms of performance statistics? And do you think there needs to be more transparency or regulation from third parties as to what's good enough and defining like thresholds for performance across so many miles?
Sure. Well, the number one design requirement at Tesla is safety. So, and that goes across the board. So, in terms of the mechanical safety of the car, we have the lowest probability of injury of any cars ever tested by the government for just a passive mechanical safety, essentially crash structure and airbags and whatnot. We have the best, the highest rating for active safety as well. I think it's going to get to the point where the active safety is so ridiculously good, it's like just absurdly better than a human. And then with respect to autopilot, we do publish this, broadly speaking, the statistics on miles driven with cars that have no autonomy, or Tesla cars with no autonomy, with kind of hardware 1, hardware 2, hardware 3, and then the ones that are in FSD beta. And we see steady improvements all along the way. And sometimes there's this dichotomy of, should you wait until the car is like, I don't know, 3 times safer than a person before deploying any technology? But I think that is actually morally wrong. At the point at which you believe that that adding autonomy reduces injury and death, I think you have a moral obligation to deploy it, even though you're going to get sued and blamed by a lot of people, because the people whose lives you saved don't know that their lives are saved, and the people who do occasionally die or get injured, they definitely know, or their estate does, that it was, whatever, there was a problem with autopilot. That's why you have to look at the numbers in sort of total miles driven, how many accidents occurred, how many accidents were serious, how many fatalities. And we've got well over 3 million cars on the road, so that's a lot of miles driven every day. It's not going to be perfect, but what matters is that it is very clearly safer than not deploying it. Yeah. So I think last question. I think, yeah. So, thanks. Well, the last question here.
Okay. Okay. Hi. So I do not work on hardware, so maybe the hardware team and you guys can enlighten me. Why is it required that there be symmetry in the design of Optimus? Because humans, we have handedness, right? We use some set of muscles more than others. Over time, there is wear and tear. Right? So maybe you'll start to see some joint failures or some actuator failures more over time. I understand that this is extremely pre-stage. Also, we as humans have based so much fantasy and fiction over superhuman capabilities. Like all of us don't want to walk right over there. We want to extend our arms, and like we have all these, a lot of fantastical designs. So considering everything else that is going on in terms of batteries and intensity of compute, maybe you can leverage all those aspects into coming up with something, well, I don't know, more interesting in terms of the robot that you're building. And I'm hoping you're able to explore those directions.
Yeah, I mean, I think it would be cool to have make Inspector Gadget real. That would be pretty sweet. So, yeah, I mean, right now we just want to make a basic humanoid work well, and our goal is fastest path to a useful humanoid robot. I think this will ground us in reality, literally, and
ensure that we are doing something useful. Like one of the hardest things to do is to be useful, to actually, and then to have high utility under the curve of like how many people did you help, and how much help did you provide to each person on average, and then how many people did you help? The total utility, like trying to actually ship useful product that people like to a large number of people is so insanely hard. It boggles the mind. That's why, like I said, like man, there's a hell of a difference between a company that has shipped product and one that has not shipped product. This is night and day. And then even once you ship product, can you make the value of the output worth more than the cost of the input, which is again insanely difficult, especially with hardware. So, but I think over time, I think it'd be cool to do creative things and have like 8 arms and whatever, and have different versions, and maybe there'll be some hardware like companies that are able to add things to an Optimus, like maybe we add a power port or something like that, or attachment. You can add attachments to your Optimus, like you can add them to your phone. There could be a lot of cool things that could be done over time, and there could be maybe an ecosystem of small companies or big companies that make add-ons for Optimus. So with that, I'd like to thank the team for their hard work. You guys are awesome. And, yeah.
Bueno, si llega a aparecer alguna otra cosa relevante acá en el video, lo voy a mostrar. Por ahora, me parece que lo mejor va a ser abrir la página de tesla.com/AI y contar un poco de cuáles son, o ver un poco junto con ustedes cuáles son las cosas que van a estar pidiendo, o los roles que se abren, ese tipo de cosas. Hola Adrian, ¿cómo va? Estoy acá con mi hermano, que juntos vamos a estar comentando un poco acerca de los perfiles que van a estar buscando, y luego dentro de un ratito vamos a estar hablando también de de la tecnología en general, de qué nos pareció y eso. Pero por ahora paso directamente, bueno, espera que te voy a sacar de acá. Tengo la pantalla de lo que está todavía mostrando el evento acá al lado, por si aparece algo. Básicamente en la página de tesla.com/AI muestran los elementos fundamentales que nos estuvieron hablando en el video: FD Chip, Dojo Chip, Dojo System, Neural Networks, Autonomy Algorithm, Code Foundations, Evaluation Infrastructure, Tesla Bot. En la presentación nos hablaron extensivamente de como los building blocks, ¿no? Eso yo les digo lo que yo interpreto como ingeniero que quisiera aplicar. Nos muestran los building blocks y tratan de que uno que quiere potencialmente aplicar a la empresa se imagine cuáles son las cosas que ellos necesitan. Entonces yo digo, bueno, necesitan gente que los ayude a pensar o a entrenar modelos, a supervisar modelos que van a ir entrenando. También necesitan mucha parte de implementación, integración de APIs, integración de un montón de cosas internas para que trabajen juntas unas con otras. Me imagino yo como programador que requieren eso. También un montón de personas que trabajen en hardware. Hardware tiene toda una rama que es dura del hardware y otra parte que es dura o intermedia, mejor dicho, que es del software del hardware, lo que se programa con hardware, digamos. Y después viene toda la parte del software que va a manejar el hardware, y cada vez más hacia lo soft. Así que hay toda una amplia gama. Después todo lo que es tagging y todo lo que es inteligencia artificial es un mundo en sí mismo. Ahí hay un montón de trabajo. Lo que yo me imagino en primera perspectiva es, no va a haber tanto lugar para gente con ideas innovadoras. Hay en este momento, o sea, el equipo de research y de feasibility ya lo conformaron. A partir de ahora solamente van a expandir esos equipos para productividad. Necesitan producir. Del lado del hardware van a producir y optimizar. Eso tiene que ver con buscar maneras más baratas y más fáciles de predecir de construir mucho equipamiento. Y desde la parte del software van a buscar acelerar los procesos, deben tener una larga lista de cosas que tienen que implementar, que ya las tienen ideadas, cómo las van a hacer, así que necesitan implementadores y no tanto arquitectos. Por eso una de las personas que me preguntaba hace un rato en el video de YouTube, acá en el chat, que por ahí no estaba como para aplicar, pero si sabes manejar modelos de inteligencia artificial, va a haber un lugar para vos. Van a buscar seguramente cientos o quizás miles de empleados. Acá seguramente no van a mostrar qué es lo que están buscando. Ahora vamos a explorar un poco, pero acá simplemente pon tu nombre, tu mail y la carta. Minimum length 40 characters. Largo mínimo 40 caracteres. Acá lo que yo pondría es: visualizo un futuro en el cual veo descender los robots de una nave que baja en Marte, preparando una ciudad y preparando el camino para que los humanos aterricemos en Marte y esté todo listo. Yo creo que con un script como ese, o algo así, soñador pero realista en el mundo de Elon Musk, ¿no? Creo que sería una muy buena carta de presentación. Después pondría un segundo párrafo diciendo: yo soy ideal para este puesto porque amo tal cosa, bla bla bla. Pones tu mejor aptitud, una o dos cosas de las que mejor hagas. Y el tercer párrafo, te hablo de párrafos de 1 o 2 renglones. Tercer párrafo pones cuáles son los frameworks que más manejás o las metodologías que más manejás. Y eso. Luego acá poner el resumen, que puede ser tranquilamente el exportado de LinkedIn si es que lo tenés actualizado, y pones a aplicar y después le rezás a tu Dios, de preferencia. Acá voy a ver un poquitito solamente careers de Tesla, pero esto no es la división nueva que están abriendo, esto es solamente la división, o sea, Tesla en general. Acá pongo View Jobs y me muestra, a ver, esto se está streameando, ¿verdad? Sí. A ver, espera que me voy a hacer más chiquita mi cara, que está súper grande. Ahí está. Acá, esto lamentablemente es un pésimo buscador de puestos porque le faltan cosas, solamente tiene la bajada de lo que tiene la empresa, como todas las oficinas y todo eso, y todos los puestos abiertos de recursos humanos, pero no te da información útil. Por ejemplo, yo quisiera saber qué puestos de los que están buscando admiten trabajo remoto, y esa información no está acá. Entonces yo pongo location, remoto, no está. Están todas las oficinas que ellos tienen en todo el mundo. Por lo tanto, si vos aplicás acá y querés trabajar de manera remota, te pueden pasar dos cosas: o tu anuncio lo va a leer alguien y va a ser desoído, o tu anuncio no lo va a leer nadie, porque van a decir: hey, aplicaste a ver a qué lugares hay, aplicaste a cualquiera, elegiste cualquiera porque total sos remoto, aplicás a Australia pero vivís en Argentina, en Bolivia, en Brasil o no sé, en Colombia, no, listo, no aplica, esto es para Australia nomás. O aplicás a Estados Unidos, United States, y te dicen no, esto es o por ahí sí, lo lee alguien y justo dice: sí, aceptamos remoto, pero como no lo aclara no sabes a dónde aplicar. Eso es muy malo. Y después los job types, nada, acá vas a encontrar desde representante de ventas en el local de Tesla hasta programador que integra APIs de pago, vas a encontrar de todo, así que esto no sirve. La cosa que ellos pretenden que hagas es que vengas acá a la página que visitamos recién, que era /AI, y apliques con tu resumen, obviamente todo en inglés, y que tu aplicación los encante. Para mí la aplicación que yo les dije recién, cómo escribir una carta de presentación que esté buena, es lo que les dije recién, son solo 3 párrafos. Si lo quieren volver a escuchar, vuelvan en el video un poco, porque ahí está, y para mí con eso va a alcanzar por lo menos para que te llamen para la primera entrevista. Obviamente todo en inglés, y que tu currículum trata de que tenga experiencias que se alineen a este siguiente trabajo que vas a estar buscando en Tesla. Si no tenés en claro qué rol podés ocupar en esta empresa, fíjate si lo que vos haces puede ayudar a alguna de las unidades de tecnología que ellos están enumerando acá. Si no tenés claro qué es lo que hacen estas unidades, volvé a mirarte la presentación, fíjate, y si no, fíjate cuál es la que más te apasiona, la que más te interesa, y aplica a esa. Y listo, menciónalo acá en tu carta y listo, básicamente eso. Hello, brother. ¿Cómo va?
Todo bien.
¿Cuál es la parte que más te gustó?
De la presentación de Elon, de Eloncio.
De la tecnología, qué sé yo.
Y siempre nos impresionan los robots, los humanoides, ¿no? A mí me encantan. Pero bueno, me parece que es un producto de marketing. No creo que vayan a poner todas las fichas en el desarrollo del humanoide.
Sabes que yo creo que va a mejorar bastante toda la parte de... O sea, como lo mejor que existe hasta ahora es lo de Boston Dynamics. Creo que estábamos todos de acuerdo. Por lo menos en lo que respecta a cómo se mueve el robot y todo. Creo que van a llegar a eso en un par de años con este mismo humanoide que tienen.
Sí. Le pegaron más empujones al de Boston Dynamics.
Sí.
Pero el resto de la presentación que hablan de las demás tecnologías me parece un poco para impresionar también, porque tienen la potencia de esa empresa de hacer microprocesadores in-house, que es algo que muy pocas empresas en el mundo pueden decir que pueden hacerlo, y están desarrollando una plataforma especial para procesar aprendizaje de máquina sin latencia, así que las tecnologías, por más que evalúen las tecnologías que un aspirante traiga, hay una academia adentro que seguramente que hay que comérsela, porque seguramente que las tecnologías que tienen están desarrolladas por ellos. Hablaron de un lenguaje que más bien parece una especie de sistema de bloques, pero bueno, en sí es un lenguaje también que usan para interpretar la información. Hay un montón de tecnología que es privativa, así que se entiende un poco lo que dice él de que quieren personas que tengan buena resolución de problemas, buenas capacidades de ingeniería, buenas capacidades, porque ¿qué va a pedir? Sí. React.
No, claro. O sea, pide gente con buen criterio, pero pide implementadores. No creo que haya lugar para alguien, quiero cambiar todo el sistema de inteligencia artificial por este otro que no está probado. Como que eso no va a pasar. Me parece que el negocio de ellos está, el apalancamiento que tienen está en la cantidad de datos que pueden procesar. Para eso hicieron esa mega computadora en el sótano. Y que el modelo de negocio seguramente va a ser un modelo de negocios por suscripción. No van a ganar plata con el hardware. Quizás el hardware lo vendan tipo a descuento, como hizo iPhone, o sea, Apple con el iPhone durante los primeros 4 años. Que el primer iPhone salía a $200, que era, es carísimo. Y hoy estamos comprando iPhones a $1.300.
Sí, totalmente.
Entonces, me imagino los modelos de suscripción como, bueno, ¿querés que sepa cocinar? Bueno, $20 más por mes. ¿Querés que sepa baldear? $20 más. Yo pienso en cosas que hago yo. O sea, no le voy a poner al bicho ese a baldear, pero en una fábrica, un modelo que no sé, que entienda cómo se comporta el agua, los líquidos, boom, $50 más por mes.
La primera aplicación va a ser seguramente lo que detonó el desarrollo incluso en Boston Dynamics, que fue el desastre de Fukushima, ¿no? Que son lugares que por más torpe que sea un robot es más útil que un humano porque no absorbe radiación. Después parece tonto, pero la exploración de Marte, que es lo que están aspirando, tiene un montón de aplicaciones para un robot, digamos. Si van a mandar equipamiento, si hay que preparar un hábitat, digamos, para futuros viajes o lo que fuere, hay un montón de tareas que no están preestablecidas porque los rovers tienen 4 o 5 tareas preestablecidas, pero si vas a armar un hábitat necesitas tener la flexibilidad que va a dar otro tipo de máquina. No creo que vaya a ser una especie de humanoide así, pero de ahí seguramente que de esa escuela, de ese desarrollo, van a sacar un montón de cosas. Y seguramente que todo lo que tiene adentro de inteligencia y demás también es privativo. No creo que estén usando, digamos, o de ellos o de Boston Dynamics.
No lo van a open sourcear, pero ni a palos. No lo van a hacer. No.
Hasta que no sean ellos first to market, no salgan con algo a la veriera, no creo. Como lo hicieron con el auto, ¿no?
Bueno, pero con el auto la ventaja competitiva tiene que ver con otra cosa. O sea, el poder de marca de ser Tesla, de ser los primeros, como que no los pueden superar. Y además arriba de eso tienen mucho desarrollo de tecnología adicional. Entonces...
Y bueno, la estrategia de cuando hicieron el auto era un grupo más chico y lo lograron sacar muy rápido. Y conforme se agrandan los grupos, caen en esta paradoja de la ineficiencia, que cada persona que se agrega o cada grupo más que se agrega a la empresa termina congestionando la eficiencia. Así que evidentemente no salen tan rápido. Creo que él mismo tropezó con los pronósticos de fechas. Claro. Por esa misma razón, porque él tenía la estimación con las 50 personas que hicieron el Tesla y terminó con 3.000 personas que no sabían ni en qué andaban, ¿no?
Claro, para cualquier persona que no lo haya vivido, que no lo haya visto en primera persona, como la ilusión de poder agarrar un equipo de 50 personas y multiplicar ese equipo tan eficiente en 50 personas más y en 50 personas más, que se te desmadra todo, porque en ese nuevo equipo de 50 tenés que tener otro Elon Musk. Y ahí es donde se empieza a complicar, porque no se puede. Ahora, lo que yo pensaba antes de arrancar a ver la presentación es qué tan lejos estamos capaz de tener una fábrica que funcione sin humanos. Porque mientras veía el video, acá en el chat venía hablando con César no sé si César u otra persona más también, que me decía que podés poner una máquina, o sea, podés hacer una máquina para un propósito específico que no tenga ningún tipo de inteligencia ni nada, pero que produzca. Digo, sí, pero la máquina en algún momento va a necesitar mantenimiento, pasan cosas, hay eventos, eventualidades, y este robot sería ideal para un escenario que dentro de todo sigue siendo controlado. No van a pasar cosas locas como que en mi casa un día me hagan una fiesta sorpresa, o no sé, en un ambiente hogareño pasan cosas locas todo el tiempo, como en la calle con el auto, como explicaban, que por eso el auto, ¿cómo se llama? El auto que se maneja solo es
autónomo,
o sea, no está en producción todavía, justamente por esa razón. Pero en un ambiente controlado como una fábrica es como que lo veo posible. Me logro imaginar y digo, tendría sentido, salvo alguna que otra intervención humana, pero bastante menos. Me imagino y trato de pensar en cuánto tiempo llegaremos a eso.
Sí, lo que tiene el robot es que puede repetir una tarea al infinito como lo vemos hoy en las fábricas. Pero después el concepto que tienen ellos ahí es el de la ciencia ficción del autómata, de la máquina que puede decidir. Y si eso fuese posible, supongo que es posible en realidad en cierto marco de trabajo, que pueda optimizar sus propias tareas, que pueda decidir sobre cuando falta una ficha, que pueda decidir cuando hay un tornillo que no está, si sigue la producción, si lo deriva a otra máquina. Esas cosas son las que no pueden ser reemplazadas todavía, que necesitan tener la cantidad de operarios que hay en las fábricas hoy día es igual a la cantidad de robots, no se redujo. El tema es que las disciplinas son otras, no ajustan tornillos, ajustan robots. Y los robots producen muchas veces la cantidad de piezas que producían los humanos. Así que de todas maneras sí se incrementó la producción, pero no es que se reemplazó la cantidad de personas con máquinas. ¿Esto qué es?
Eso es la competencia esta es desde el 2015 ya, una competencia de la que hablábamos hoy, que probaban qué robot puede llegar hasta un rincón y cerrar una compuerta de agua que es para desastres.
Claro, en Fukushima el problema que tuvieron fue que había que cerrar una válvula que estaba imposible de acceder para los humanos y no había un solo aparato que pudiera hacer esa tarea tan simple. Y terminaron haciéndolo personas que se turnaron en una tarea terrible, ¿no es cierto?
Sí, contaminante, tóxica.
Y eso, digamos, disparó esta carrera, pero quedó un poco en la nada también, porque no vi nada en el mercado. Vi uno que sí, que pasa escombros y escaleras, otro que cierra una válvula, pero no que llega a la válvula, que sortea los obstáculos.
Nada, era muy gracioso verlo porque los ves caerse, los ves fallar directamente. Lo que yo me imagino es en unos cuantos años podríamos llegar a ver estos robots de Tesla en algunas fábricas puntuales y después ya flasheo totalmente con... Qué lindo que era este, ¿eh? Después flasheo totalmente con imaginarme naves bajando en Marte con los perritos estos, los amarillos, con los robots de Tesla y con las máquinas de boring machine que apenas llegan se ponen a hacer túneles. La primera ciudad en Marte va a ser subterránea, absolutamente. Y nada, preparando todo eso para cuando lleguen los primeros.
Y tiene más margen de error el cuadrúpedo porque tiene 4 patas, 4 puntos de apoyo, tiene más estabilidad.
Y sí, la verdad que para fábrica lo veo más.
Pero en Marte, si eligen bien el lugar, la mayor parte la van a poder hacer con cadenas y con ruedas, así que no van a tener la necesidad de llevar miles de estos. Seguramente que van a ser para cosas específicas, como cuando se les trabaron, hay 2 rovers abandonados porque no pudieron salir de la arena, así que...
Claro. Hay que
primero a recuperar esos rovers.
Claro. Daniel dice, no me imagino un robot cambiando un rodamiento de un motor o haciendo una ruta de lubricación o haciendo una reparación mecánica. Para mí, ese es como la mayor utilidad que le podría ver a uno de estos autómatas, porque agarrar una caja así y llevarla a otro lado, o agarrar una regadera que está posicionada en el centro de la mesa, la regadera ponerla atrás de la plantera y que de ahí la agarre, si es tan bueno.
Claro, lo que dice el rodamiento tiene mucho sentido, porque como tienen interferencia mecánica, no hay lugar de error, no tiene un lugar de error para meter el rodamiento en el lugar. Entonces, claro, necesita que sea realmente preciso el robot. O sea, el píxel ya es grande para lo que vería el robot. Necesita algún otro mecanismo u otro sensor para poder funcionar. Pero bueno, son desafíos que para mí son desafíos técnicos. Las dificultades más grandes no creo que estén ahí. Están en que sean automáticos a la hora de tomar decisiones. Que puedan decir, por este lugar parece que es peligrosa la arena, sin probarla, sin verla, y rodear el lugar para no hundirse. Esas cosas son las más difíciles, me parece, a nivel software o a nivel ingeniería de software.
Sí. Yo me imaginaba hace un tiempo, antes de esto, ¿no? Hace 5 o 6 años te digo, ¿vieron viste los coreografías que hacen con los drones? Yo me imagino que vos podés tener drones en una fábrica que agarran cosas de un lugar a otro, y en un ambiente hogareño hasta podés tener drones con elementos puntuales abajo, garras y cosas que te laven los platos y que te hagan cosas también.
Sí, totalmente. Que te alcance el control remoto.
Le tenés que dar, tienen que tener la inteligencia para saber qué hacer y cómo cooperar unos con otros, nada más.
Sí.
Y después tenés un stack donde se van posicionando para cargar las baterías y listo.
Sí. Hay una charla TED vieja ya, que mostraban 3 de estos con una red, con una malla, y orientaban la malla y arrojaban una pelota, pero con una precisión impresionante. Y es viejo el video, bastante viejo. Pero era lo que decís. Dentro de una habitación, habían puesto una red para el público por la duda, pero dentro de esa habitación, con absoluta precisión, esos 3 drones funcionaban como una sola entidad.
Claro, me acuerdo que buscaban el equilibrio de algo, ¿no? Entre los 3.
Y hacían varias cosas, sí, es verdad. Tenían varias funciones.
Pero entre varias unidades, si tienen un peso, pueden juntarse y golpear una puerta, o sea, pueden hacer muchas cosas. No hace falta
Sí, vi últimamente una implementación de drones que viene cubierto con una malla, como una tela como esa de los parlantes, que es muy liviana. Y la idea de ese dron, que las hélices están protegidas, es que recorra estructuras dañadas para hacer un primer análisis. Entonces entra en edificios después de un terremoto, teniendo un set armado, ¿no?, de prueba. Y para hacer un primer análisis de daños y demás, y no meter un humano. Sí, obviamente para moverte a través del aire es mucho más fácil que lograr un bípedo que tiene que resolver un montón de problemas motrices.
Bueno, la empresa esta para la que trabajé, que es de la industria de la robótica, la primera cosa que hacían ellos, antes del producto que intentaron hacer conmigo, era hacer estos como assessment de seguridad en ambientes tóxicos. Entonces entraban a una planta nuclear que estaba suspendida, por ejemplo, y navegaban todo con los drones con un escáner LiDAR, y después analizaban los datasets, no sé qué buscaban puntualmente, pero eran como unos análisis de calidad que hacían en centros. Y después de eso...
¿Y mapeaban el lugar?
Mapeaban el lugar. Cuando vieron lo difícil que era pasar el log del robot, que la mayoría, este no, porque tiene su propio sistema operativo, pero hasta ahora todos los otros robots, porque el auto autónomo es un robot también, pero la competencia, como el auto de Uber o otros, no me acuerdo los nombres ahora, pero que los ves andando por ahí por San Francisco testeando los sensores, lo que cuesta, o sea, todos usan ROS, Robot Operative System, que es un flavor de Ubuntu. Cuando tratás de sacar el log es una batería de datos, tiene video, tiene LiDAR, tiene logs, tiene todos los sensores marcados por tiempo, está todo sincronizado por los tiempos, entonces vos agarrás un slice, pero cada slice pesa gigas y gigas, entonces ya solamente mover el log de un robot a la computadora para analizarlo es muy difícil, y el producto que quisieron armar en RavenOps era justamente eso, un pequeño pedacito de software que lo pones en ese ROS, en ese Ubuntu, en el robot, que te hace el slicing y te lo sube a internet, te lo sube a la nube, y desde el data center descargábamos ese pedazo y teníamos el dashboard para visualizar todos los sensores, todo el LiDAR y toda la cosa. Eso era como el producto que al final falló, pero bueno, ese era el producto.
Ahora, a los robots, a los autómatas o robots se les exige, se los compara con el humano, pero ni siquiera se los compara con el humano promedio. Se los compara con el mejor ser humano y tiene que superar al mejor ser humano. Entonces, si vos querés comparar a este robot que estamos viendo con un hobo de San Francisco, lo largas con un sobre todo y nadie se da cuenta.
Y lo peor es que va al correo y se afana una caja y la agarra así.
Sí, es un hobo, pero es que ahí me doy cuenta, cuando agarra la caja es un hobo llevando sus cosas de una esquina a la otra.
A ver, Daniel dice, supongamos que se alcance ese punto, la visión del mantenimiento va a cambiar totalmente. Si me imagino humanos reparando robots, obviamente ese personal va a tener que ser muy calificado. Sí, para mí está buenísimo imaginarme un mundo en el cual decir, che, que el trabajo lo hagan los robots, y después que el trabajo más avanzado lo hagan los humanos, hasta que algún día los robots puedan hacerlo. O sea, por favor.
Sí.
Porque la gente sigue luchando por tener trabajo, y lo entiendo, porque es una cuestión de supervivencia, pero es como que si nos organizamos, podemos mantener ese modelo, digamos.
Claro. Si conseguimos que todo el mundo tenga un propósito y no sea trabajar, pero que tengan un propósito. Ahora, el tema del mantenimiento, cuando se decida que no haya mantenimiento, las cosas no van a tener más mantenimiento. Digamos, existen piezas sin mantenimiento desde siempre. Son muy caras de manufacturar y aparte no ayudan al negocio de producir bienes porque no tienen mantenimiento. Tienen el negocio secundario, lo anulan completamente. Pero cuando mandan, por ejemplo, articulaciones al espacio, que están en un ambiente absolutamente hostil, la vida útil de esas articulaciones es prácticamente infinita. No tienen, porque están diseñadas para no tener mantenimiento. Si te pones a pensar, los rodamientos, ciertas piezas de los automotores, por temas de seguridad, son indestructibles. Y hay otras que son prácticamente indestructibles. Si mirás el rozamiento que tienen las piezas del motor y duran 200.000 kilómetros o 300.000 kilómetros sin tocarse, te das cuenta que una rodilla podría durar eso, o un codo, si se toman las determinaciones. Entonces son métodos de fabricación y ya existen. En un montón de maquinarias y piezas se usan. En las armas se usa mucho también.
Sí, estaba pensando en el tungsteno y en todos esos metales raros, que claro, te pones a manufacturar también piezas que duren mucho y se te acaba la materia prima, me imagino.
Y se te acaba el segundo. Y acá no tiene sentido porque te autoinfligís un daño, porque no tenés un negocio secundario del cual va a vivir un montón de gente también. Sí. Entonces, digamos, funcionamos de una forma no la más óptima, sino la que nos conviene un poco a todos.
Claro.
Entonces no es práctico. Pero si hace falta, aparecen esas piezas, digamos.
Sí. Es como que yo pensaba, cuando éramos chicos, o nuestros padres todavía, los juguetes que tenían, por ahí un nene tenía un triciclo y el triciclo duraba añares y lo heredaba el hermanito y lo heredaba y todavía sigue, está ahí guardado y sigue funcionando. Y ahora no, ahora compras un triciclo y lo dejas guardado y lo vas a ver la siguiente vez y está todo oxidado, decís, ¿qué le pasó? Entonces la obsolescencia programada combinado con abaratar los costos de la manufactura, vienen de la mano y siguen produciendo y todo. Pero estaría buenísimo tener una fábrica multipropósito con un montón de máquinas que no sean para un propósito específico, sino multipropósito, y que digas, ¿sabes qué? Estos próximos 5 años, generar la próxima tirada de juguetes que van a durar 3 generaciones. ¡Boom! Ya está. Y no es un negocio, es una cosa que la humanidad necesita. En vez de esto de producir, a mí me espanta la cantidad de basura que tiro. Y tiro poca basura, ¿eh? Pero cada bolsa es tipo, ¿qué es todo esto? Esto va a durar miles de años como sombrero de un delfín, como decía.
Sí, totalmente.
Louis C.K.
Pasa que cuando se analiza eso se piensa que falta mucho para que esté saturado de basura todo, y en realidad si es que en algún momento va a pasar, hay que atenderlo hoy, pero son temas ya rozan lo filosófico. Hay gente que no lo va a tomar en cuenta y va a seguir priorizando el negocio, el mantenimiento, el aceite. El aceite es uno de los contaminantes más pesados que hay, porque no lo que más, digamos que la atmósfera es bastante noble con la nafta, porque se lo lleva más lejos, digamos. Pero el aceite, para disponer del aceite, muchas veces no quieren gastar dinero y lo terminan tirando en lugares que no se debe y es sumamente contaminante. Entonces sí, el negocio está siempre molestando esto, ¿no?
Sí. Pero bueno, le tengo fe al emprendimiento, a la startup esta que está tratando de armar.
A la startup, la pyme de Elon.
Sí. Le tengo fe, me parece que... Quiero decir, el leverage está en la cantidad de datos. Eso que estábamos viendo en pantalla recién,
sí.
La facultad de poder tener, no te digo en una fábrica, no sé, acá cerca por ejemplo hay una fábrica que hace como cosas de baño, como la bacha del baño, inodoros, bañeras, cosas así. Es una fábrica común y corriente. No te digo meter 20 robots en esa fábrica. Te digo meter miles de robots en cientos de fábricas y que vayan viendo cosas que son similares y uno diga, esto es un perfil de aluminio, como hay en las otras 80 fábricas y entre todos se van como nutriendo y entendiendo qué son los objetos, cuál es el significado de cada uno de los objetos y todo lo demás, y aprenden así a navegar y a hacer cosas que sean multipropósito.
Claro.
Eso lo veo.
Eso es interesante, porque a un ser humano no se le muestra toda la ciudad en fotos para que sepa moverse por la ciudad. Tiene unas reglas fundamentales para no caerse, cómo funcionar, digamos, cómo funcionar sin obstáculos a su altura, pero con cordones de vereda, con cosas mínimas. Y el resto son comandos muy básicos. A una persona le podés decir, no vayas a tal lugar que es peligroso, o salí con paraguas porque va a llover. No se le dan instrucciones precisas, son instrucciones y no necesariamente lleva años aprenderla. Una vez que aprende a caminar, que es un tema muscular, de estructuras neurales, de estabilidad nada más, una vez que logra ser estable, los demás comandos son simples. Entonces, esta forma de que sea por fuerza bruta y demás, es complicado de escalar. En la conversación, en la presentación que hicieron, justo antes de mostrar la nueva plataforma que tienen de hardware para aprendizaje, dice, tenemos esto, movemos toda esta cantidad de información y más, y esto no escala. Y en robótica esa frase es muy repetida. Esto no escala, porque están al límite del flujo de información que pueden manejar y están en un lugar confinado, digamos, pues están en un lugar controlado. O lo que hacen con el auto, procesan offline. Entonces no se puede hoy día, por eso están creando hardware, pero el hardware va a mover toda esa cantidad de información. Ahora, evidentemente no han logrado generar un algoritmo que pueda resolver con pocas instrucciones situaciones complejas. Por algo lo hacen de esta forma con fuerza bruta. pero con el tema del video que está justo en pantalla, de la estabilidad del bípedo, digamos, de la estabilidad, es que cualquier comando que se haga para corregir un movimiento de estabilidad, eso pasa en los aviones también, en los autopilot. Tiene un tiempo, aunque no sea perceptible para nosotros, tiene un tiempo de demora. Y el actuador tiene, después del EMF del motor y demás, tiene un tiempo de respuesta al motor y hasta que acomoda la pieza y demás. Todo ese tiempo tiene que ser computado para ser absorbido por la corrección que se va a hacer en el siguiente paso o en la estabilización de estar parado. Eso es sumamente complejo, son cálculos muy complejos, son algoritmos muy complejos, y parte del aprendizaje del robot cuando camina es estabilizarse. O sea que es todas las posibilidades que ellos usan tensores, que es una estructura que tiene la interrelación de dos nodos en el espacio, digamos, que va analizando y dibujando esa lineecita. Ese aprendizaje, que para nosotros es tan natural, al robot le cuesta un montón, porque tiene que predecir esos micromovimientos para estabilizarse, porque no puede hacerlo en tiempo real. Bueno, entonces, estamos ahí parados en un lugar tan básico para querer resolver problemas súper complejos.
Claro. Sí, por eso a mí me gusta la integración de hardware que sea autónomo. Es como que el equilibrio de la cadera vos ya lo tenés, no lo pensás con la mente. Es como que lo pensás con la cadera.
Y tendrías que tener chip en la cadera.
Claro, y en todo caso
resuelva ese movimiento.
Claro, en todo caso que la cadera le informe a la cabeza ante alguna eventualidad, pero nada más.
Pero el enfoque sería diferente. Necesitarías un equipo que te haga la cadera y que solamente se dedique a eso y sí.
Escenarios que, ¿cómo es? Inesperados. Un camión parado, volcado, lo que el auto debería haber hecho, y lo que el auto hizo fue comerse el camión a toda velocidad, ni siquiera atinó a frenar. No sé si vieron este video, a ver si bueno, este chico lo está como explicando el caso en vez de mostrar el accidente. Y... sí, ahí está. Viene... Boom. Atinó a frenar. Pero nada, no dobló, no hizo nada. Entonces, eso, o sea, inevitablemente va a pasar, y en la fábrica, cuando estén los robots, también. No es que vas a poder reemplazar a todos los humanos, por lo menos no con este approach de tecnología, y el approach que yo lo decía hoy en el video más temprano, me lo confirmó él mismo diciendo, no, de todas maneras esto es safer than humans driving. Estadísticamente va a ser más, pero estadísticamente una persona nunca se hubiese comido ese camión. Bueno, capaz sí, algún distraído.
Si se duerme únicamente. No funcionando, porque el robot estaba alerta. Claro. Una persona alerta no se lo come.
Dice Daniel, las centrales de biomasa, si bien actualmente su materia prima es la materia orgánica, se está estudiando sistemas similares de biomasa, pero aplicado a los residuos, generalmente plástico. En el futuro a mí me encantaría investigar o dirigir un laboratorio de investigación que divida la basura en sus componentes primarios para poder reutilizarlo, porque a futuro eso es el quilombo que se... Y además está lleno de materiales que son útiles. Cáscara de banana... No, bueno.
Hay comida, hay menús de McDonald's.
No, metales, tierras raras, es un montón, cosas electrónicas.
Me acuerdo cuando habían investigado estas bacterias para que se coman el poliestireno.
Sí.
Y hoy día las bolsitas tienen muy poco poliestireno, son una mezcla de reciclajes de otras cosas que quedó nulo el experimento. A menos que usen materia virgen, lo cual no es ecológico.
Claro. Y bueno, ahora hay como nuevos materiales plásticos que los sacan de plantas, los sacan de caña de azúcar u otras, y no de petróleo. Mira, esto es lo que decía hoy del autotagging, porque esto que tiene acá de las cajitas es como una representación cruda de lo que ve, pero lo que está pintado de verde es o tagging offline o autotagging. Pues tranquilamente esto podría haber sido una persona pagada que viene y pinta como con el paint, pinta todo el área que cubre el humano en 2D. Y cuando vos lo ves, no sé si lo mostraban por acá, acá, al robot interactuando, Está buenísimo, ¿eh? Y obviamente no digo, esto es una truchada. No, está increíble. Lo que hablo es de esto aplicable al mundo real. Lo muestran acá. Ahí. Muestran lo que él ve. Que sin dejar de ser impresionante, no tiene el nivel de precisión que requiere el trabajo que uno tiene con las manos. O sea, agarrá este lápiz y escribí algo. Muy difícil.
Fíjate cómo cuando se mueve se amaca hacia el lugar donde no logra frenar con precisión, porque todo lo que tiene que ver con la compensación de los movimientos no es parte del algoritmo. Por eso lo compensan, valga la redundancia, haciendo que se mueva muy de fuerza para frenar el movimiento, pero con muchísima precisión. Y no lo hace el robot, digamos, se ve que no lo hace.
Sí, pero yo lo tomo como un first draft al robot. Yo no creo que eso se hayan puesto a trabajar en eso. Porque, ¿sabes por qué? Al principio lo vi y dije, mirá cómo mueve los brazos, así. Pero después lo mostraron en el modelo simulado y lo tenían en el modelo simulado antes de que pase. Entonces, es así por diseño, en el sentido de decir, no lo vamos a implementar todavía, esto que mencionaste recién, de compensar con el peso, con contrapeso del cuerpo, porque requiere mucho trabajo hacer eso.
Y muchísimo poder de cómputo, solo para eso.
Sí. Quiero ver si muestra la parte en que él agarra el pedazo de aluminio y se ve lo que él ve, lo que él interpreta con el auto tagging, que son como un cuadrado rosa que va haciendo esto más o menos arriba del aluminio. A ver, John Sheff dice, ¿se pensará en reemplazar sistemas primarios de defensa, ejército por robots? Que no suceda. Y eventualmente sí, ¿no? Pero,
lo que pasa es que ¿dónde está el poder del poder de daño si vos estás dañando robots? Digamos, el poder de daño que tiene la batalla es que va a dañar humanos y eso fuerza por ahí una negociación o algo, o sea, deja de tener sentido. Que sería divertido de ver, sí, pago yo primera fila porque quiero ver una pelea de robots.
Claro.
Pero estilo Chapi estaría genial, ¿no?
¿Qué hacía Chapi? Disparaba así,
¿no? Era un boxeador.
Boxeador.
Sí.
No más guerras, sería una locura y sí, pero bueno, no sé si eso el ser humano es como que...
tiene que surgir un negocio que la reemplace.
¿Cómo? Acá tiene que aparecer, yo lo vi eso en el video de hoy, ¿lo cortaron? ¿Este es un video recortado?
¿O sería en la simulación?
Este también tiene 6,50. Pero bueno, se entiende lo que decía, ¿no?
Que se ven los cubos, digamos.
No los cubos, pero es como que el autotagging pinta...
Lo colorea, claro.
Pinta por encima, más o menos.
Sí. Yo lo que creo es que esto deben haber tagueado a mano y la pintura puede ser automática del verde, pero... lo más probable es que sean tallados a mano. Tampoco vas a saber si no tienen un tinte para ser levantados con ultravioleta. Sí. Puede ser también.
No hay nada.
Entonces,
Ahí está.
Ahí está. Mira, para la demostración tranquilamente pudieron haber usado pinturas con reflectividad según el rango de color que quieren reflejar, ¿no es cierto? O sea, con ultravioleta o con algo de eso.
No hay
Así
nada,
que...
No hay nada que me ponga de peor humor respecto de la inteligencia artificial que ver un robot agarrando una caja con un QR. Ay, Dios, qué vergüenza ajena que me da eso.
Bueno, pero para reemplazar el QR podés usar algún otro esmalte que lo levantás con otro tipo de radiación como ultravioleta. Si vos agarrás ácido acético y ácido, ¿cómo es el de la naranja? Cítrico, tienen diferente color con la luz ultravioleta.
Mirá. O sea, él interpreta que más o menos en ese lugar está el elemento, previamente tagueado y previamente encastrado en estos rieles de madera, y es como de toda una cosa, ¿no? Muy rudimentaria, pero igualmente...
Precisión Hobo.
Pero nada, o sea, lo que sí tomé de la charla era, estos son los building blocks. Construimos el hardware, tenemos la máquina, tenemos el modelo, tenemos las cosas, ahora hay que integrar todo esto, hay que implementar. Me parece que yo lo vi de esa manera, y si va a funcionar, cómo funciona el FDS en un entorno privado, pues si vos decís, yo tengo un campo de golf, ponele, y yo soy el dueño, y yo permito que adentro de mi campo de golf se use el FSD, ¿cómo se llama? Es que se manejen solos los autos sin chofer, es un ámbito privado. O sea que ahí se puede. Entonces, tener eso en una fábrica que es un ámbito privado, le tengo la refe. Me parece que en 3 años, 5 años, 3 años, y Adrián decía en 3 años Elon Musk, que son como 6 años.
Sí.
Pero lo veo sucediendo, a full, de una. César dice, esas pintadas son con algoritmo de computer vision, modelos de segmentación. Son populares desde hace bastante tiempo. Algunos de los modelos más recientes son el segformer. No son perfectos, pero han mejorado bastante. El input es solo la imagen no hay ningún tipo de luz ultravioleta o similar. Es solo la imagen del input. Claro que esa es el...
Pero se identifica, digamos, manualmente, o por ejemplo, cuando en el dron elegís un target para seguir, lo identifica una vez que lo tagueás, digamos. Le encuentra sus márgenes, encuentra su perímetro, pero tenés que identificarlo, digamos, primeramente. No reconoce la forma humanoide, no reconoce la forma de lo que querés seguir, pero una vez que tagueás,
claro.
A eso me refería. O la otra sí es ponerle algún otro tipo de codificación, pero las dos... Sí. Para una demo, las dos son válidas. Claro. Porque la demo intenta vender un poco la idea, ¿no?
Pero el dron, que detectará color o contraste o algo así.
Yo creo que es contraste, porque hace una especie de...
Cuando busca puntos de contraste cercanos al lugar donde hiciste clic, algo así.
Claro, una vez que elegís una zona, lo que va a hacer es buscar un perímetro, buscar lugares de alto contraste o de alguna forma identificar eso, seguirlo.
Sí. Después nada... ¿Qué?
Cuando se pinta dinámicamente, en general se ve un poco diferente la imagen, porque no tiene a menos que sea una imagen 4K y sea tremendamente precisa, pero tiene su pequeño defecto, porque no se busca con el algoritmo generar una delineación perfecta, se busca identificar las imágenes y usar ese poder de cómputo para otra cosa más útil. Bueno, así que también es llamativo eso.
Pero claro, el punto es que el cambio de scope que hace el ser humano cuando está haciendo algo en una fábrica, uno pasa de algo muy grande a algo que requiere mucha precisión. O sea, de repente, movés una heladera con alguien que te ayuda, y depende de cómo la agarres, depende de eso si haces mucha fuerza o poca fuerza. O sea, hay muchas cosas que requieren maña y un aprendizaje que uno ya lo tiene intuitivo de haber vivido en esta gravedad durante tantos años.
Totalmente.
Entonces, ¿cómo haces para pasar de... Puedo decir, sí, bueno, agarrar un fierro, ok, listo, para eso con una topadora también lo agarras el fierro. Pero necesitas como ir a lo preciso y ajustar una pequeña tuerquita que está dentro de algo.
Cuando vas en el avión y se te cae algo al piso y tenés que llegar al piso así con la absoluta precisión con 2 dedos y levantar la pieza, bueno, esas cosas sí son muy difíciles de resolver. Nosotros conocemos sentimos nuestros límites en las articulaciones, y como son flexibles, como que tienen un poquito más. Hay un montón de dificultades que no tenemos.
Sí. Daniel dice, una pregunta: un robot en Marte con una gravedad distinta, ¿los cálculos deben ser distintos? O sea, me imagino la imprecisión de un robot hecho acá, probado allá. Y además, no solo la gravedad, me imagino que quiero decir, no me imagino que solamente cambiándole la gravedad vaya a funcionar. Tiene que reentrenarse en esa gravedad, porque van a haber un montón de cosas que son distintas.
Seguramente que va a ser muy diferente.
Y después César dice, digamos que el modelo está entrenado con muchos labels. Por ejemplo, en el del autopilot está entrenado con muchos labels o clases por tipo: auto, semáforo, árbol, pedestrian, etc. Lo que el modelo hace... creo que está escribiendo todavía. Respecto a lo que hablábamos recién, que dice, el input es solo la imagen, no hay ningún tipo de luz ultravioleta o similar.
Claro, sí, sí, por supuesto. Digamos, no se puede dudar de que eso se puede hacer. Lo que yo estoy dudando es de esta demo, nada más. Porque hemos visto desde las primeras versiones en el 98 que identificaban bolsas en los aeropuertos, hasta hoy mejoraron, y en esa época ya era bastante preciso, digamos. Hoy mejoraron un montón. Pero bueno, la verdad es que para ver un producto que sea viable, por lo menos para ponerlo a prueba en un trabajo, tiene que cumplir con muchas cosas más que las que... O sea, tiene que ser seguro, tiene que identificar, no ser peligroso para un humano, tiene que identificar sus límites. Hay un montón de cosas. Después hay temas mecánicos que no tenemos nosotros. Bueno, sí, pero lo sabemos controlar. Temas térmicos.
Sí. Y César dice, es que toma una matriz que representa los píxeles de la imagen y te devuelve otra matriz del mismo height y width, pero con números identificadores que te dicen a qué clase representa cada píxel. Claro, pero el punto es que mientras lo estaba viendo ahí en pantalla, que eligen algunos frames para hacer esa representación, en algún frame es así, en otro frame se mueve un poco, es como que hace el wiggle
Pero claro, es adrede para no gastar tanto poder de cómputo en algo que es tan insignificante.
Sí.
Como las líneas de la calle, ese es un buen ejemplo. Cuando se ve que se mueven, bueno, tienen una superposición de probabilidad, o sea que usan la probabilística para que el elemento que cayó en un píxel en una no sea dominante sobre el elemento que cayó en un píxel de otra imagen, sino que va por ahí. Toma.
Claro. Y después decía respecto de los escenarios que son distintos, en la autopista anda re bien, porque en la autopista lo normal es que todos estén avanzando y que a veces todos estén quietos. Cuando pasa cualquier excepción es un potencial accidente y hay que evitarlo. Lo que es difícil es este escenario. Bueno, y acá todavía hay semáforos que dentro de todo son fáciles de detectar. Ahí. Lo que decía es, detectame el semáforo que está acá, que está en diagonal y está colgado así, y una luz ni siquiera es totalmente roja. Sí. Eso no lo va a ver jamás. Me cuesta verlo a mí. O sea... nada, en estos escenarios. Pero bueno, por eso te digo, si vos sos el dueño del barrio o el dueño de esta intersección de calles y decís, en mi entorno privado habilito el manejo, que se maneje solo automáticamente, el FSD, ya está, adentro de tu propiedad privada haces lo que quieras.
Claro, totalmente.
En America.
Bueno, pero para que los autos sean seguros, los autos que usamos hoy día sean seguros, la infraestructura tuvo que cambiar muchísimo, porque sobre tierra no eran seguros y demás, crearon asfalto, sobre empedrado no eran seguros. O sea, podría esperarse que la infraestructura de las ciudades se acomode y no sea tan hostil con los autos autónomos, que se acomode y generen reglas por ley, digamos, que tengan cordones pintados, y que el auto resuelva las excepciones. Hoy día el mundo es una excepción.
Claro. Sí. O sea, vos decís como decir que no reemplace al conductor, que el conductor siga, pero que el self-driving sea un asistente, digamos.
Pero la ciudad debería acomodarse para no ser tan hostil con los sistemas de manejo autónomo. Sí. La ciudad debería tener, porque como hay señales para nosotros, podría haber señales para... Obviamente todo puede ser mal usado por alguien con malas intenciones. O sea, el auto tiene que tener...
Pero las señales pueden ser... o sea, así como hoy hay semáforos, podrían haber unos tótems que emitan una señal por Bluetooth o por alguna otra radiofrecuencia a qué lane está en luz verde y cuál no. Había un chabón, había un tipo que no me acuerdo quién era, pero me parece que era chino, que decía, o de Singapur, no sé de dónde, y decía, la manera más barata para sistémicamente resolver el problema de los autos autónomos es dibujar una línea azul de 30 centímetros de ancho en las lanes. Con eso resolvés todos los problemas. Porque es tipo, lo mandás por un track, que la ve, la línea, y ya está. No tiene que estar mirando e interpretando dónde hay una esquina, dónde hay un cordón. Es muy difícil eso.
Eso en conjunción con algún otro elemento para que nadie venga a pintarle una línea y llevárselo a su casa, al auto, ¿no?
Claro. Vas con el baldecito ahí adelante del auto, pintándolo.
Pero sería, obviamente, sería una gran ayuda porque solamente resolvería los casos excepcionales. No debería estar resolviendo todo el tiempo. Y la carga de proceso de eso sería menor, porque una vez que identificas tu identificador principal, no necesitas, si bien vas a tener lectura de algo que te dé soporte, no vas a tener que tener esta cantidad masiva de información saturando todos los sensores, ¿no es cierto?
Sí. A mí no me gustó que saquen los lidars del auto. Me parece que, aunque estoy de acuerdo en el approach de decir que toda la información la tomen por video y que de ahí interpreten el mundo, no tenés por qué desestimar una información adicional que es mucho más avanzada de lo que cualquier humano podría llegar a ver jamás. Como sumarle
totalmente
eso
de acuerdo.
a esto. Está.
Nunca una lente va a ser tan precisa como es el láser. El LiDAR es lo más preciso que hay. A nivel distancia y foco no existe otra cosa más precisa.
Entiendo que tenés falsos positivos, como que justo el LiDAR pase a través de un agujerito de un camión y no lo vea, ponele.
Sí, pero hace barridos el LiDAR, así que es muy difícil que eso...
Sí.
Hace barridos. La magia de la lente, de interpretar distancias en la lente, hay un sector en el medio que es más o menos creíble, pero en las esquinas, la imagen que vemos es absolutamente compuesta digitalmente. Esa lente deforma las esquinas. Si vas a usar una imagen que está recompuesta para hacer cálculos de los cuales puede depender la vida de una persona, es muy riesgoso. En ese caso, el LiDAR no tiene errores, porque usa las coordenadas polares, no tiene defectos de lente, porque mueve la lente con el láser. Una vez que calibraste la lente, no cambia. Así que tiene muchas ventajas, pero es más lento.
Claro. Me acuerdo que yo probé la primera versión del FC, se llama, ¿no?
Ah, sí.
FC, que todavía no veía semáforos ni nada y no andaba muy bien. Pero igualmente te seguía la lane, te hacía un montón de cositas y estaba bueno. Ya que ande solo por la autopista, ya es un 20 eso, es un montón.
Ya que sí, que funcione como un asistente es muy, muy bueno. Sí. Ya que haga un frenado de emergencia o que ayude cuando te cruzas de lane, es tremendo. Que pueda ver el semáforo, que es relativamente sencillo si no está chocado.
Pero ponele que no, que en ciudad no. Yo te digo, soy feliz con dos features. Uno, que ande solo en la autopista y que en el estacionamiento del shopping me deje en la puerta, se estacione y me pase a buscar. Esas dos cosas, ya está. Estoy contento.
Sí, que sepa bajar volviendo de Richeri a Capital, que sepa bajar en General Paz, sería como una prueba terrible. Claro. Y salir de una rotonda...
Sí, que sepa
por acá.
Que sepa ignorar la luz roja a la madrugada en el conurbano para que no te afanen.
Sí. Y si le gana el carril a un taxista, ya está. Puede ir a Marte ese auto.
Que le tire el auto a un motoquero.
Claro, ya está. Sacarle el cerebro.
Modo argentino de FC.
Modo Latinoamérica.
Sí. Así que bueno. Bueno, ¿algún comentario más o idea que quieras debatir o dejar?
No, fue muy divertido.
Sí. Nada, tengo ganas de ver más adelante cuando realmente vayan a hacer una presentación de producto. Y está buenísimo.
Tienen que pelear con el de Boston Dynamics. Tienen que armar una pelea ahí con...
Claro, pero el de Boston Dynamics lo abandonaron.
Sí.
O sea, no es que lo abandonaron, pero la empresa se vendió y pasó por varias empresas y ahora es de Samsung.
Claro.
Y es un cascarón vacío el robot ese ya. De hecho, cuando ves la evolución, el robot cuadrúpedo que armaron no tiene el equilibrio dinámico que tenía el primero. El primero, que era ese que tenía el generador arriba y todo,
Sí.
que lo pateaban, ese tenía un equilibrio dinámico 100% real. El de ahora no. El de ahora se basa su equilibrio en dejar los servos quietos. Y si bien si lo empujás compensa, su equilibrio principal se basa en quedarse quieto. Si lo mirás, y es una gran decepción. Eso, sí. Lo otro gastará mucha energía, calculo, por eso lo sacaron. Pero
Ahorran energía, pero no, sí,
No
pero
está
le perdieron la naturalidad que tenía, ¿no?
Sí. Y después, ¿cómo se llama? Está buenísimo ver que la empresa entera no gasta plata en marketing. Entonces todos estos eventos son también una vuelta de rosca del marketing y del hype y del todo. Muy interesante, desde el punto de vista de negocios, desde el punto de vista de marketing y desde el punto de vista de tecnología también. Porque si no te permitís soñar en algo que muchas personas piensan que es imposible, la innovación no va a aparecer nunca. O sea, si vos te quedás en lo que muchas personas dicen, no, todo esto es re difícil o es imposible, ya listo, ni nos esforcemos. Así que en eso la verdad, un aplauso.
Totalmente. Y también muestran que como empresa soportan a los desarrolladores que traen ideas, digamos, porque muchas veces no tenés mucho rango para fallar en una idea. Cuando vos inventás algo nuevo, puede ser totalmente basura.
Claro.
Así que ese es un buen mensaje también de marketing, digamos. Vengan acá, lo que dijo al final, nosotros no vamos a hacer, no me acuerdo de la palabra, que es el engaño del chupetín. Las empresas que engañan con el chupetín.
Honeypot,
Sí, algo así, que te traen a trabajar con un montón de promesas, como esos chistes que hay en los videitos de tenés vacaciones ilimitadas. Bueno, eso sería 2 semanas.
Claro. Sí. Corporate.
Entonces,
la nueva Corporate America. La nueva empresa corporativa.
Exacto. Entonces, eso es buen marketing también para ellos, si quieren hacerse de buenos cerebros, ¿no?
Sí, también decía que, que vas a usar tu talento para hacer algo que sea significativo para el mundo, que eso es muy importante, y esa es una cosa que en Tesla utilizan mucho ese argumento. O sea, la mayoría de la gente que trabaja ahí tiene que estar ahí por la misión, no por la plata, porque de hecho no es...
Claro.
O sea, un ingeniero que trabaja en Tesla puede ganar más plata en otra empresa.
Claro.
Eso lo sé porque trascendió en internet, o sea, no es que yo lo conozco a alguien que trabaja en Tesla ni nada.
Pero la verdad es que si te gusta lo que haces, trabajar en Tesla te da una sensación de una satisfacción muy grande, seguramente. Sobre todo si respetan lo que haces.
Sí. También tenés que estar en un buen equipo y todo, porque es muy difícil que te toque, habiendo tanta gente, que te toque hacer algo trascendente, es difícil. Por ahí te toca revisar un modelo de AI que no hace nada interesante y es un embole total.
Se puede pasar, sí. Pero si sos parte de un equipo que hace algo importante como equipo...
Sí. Ni hablar. Así que bueno, voy a cortar, me voy a picar algo y me voy a dormir.
Bueno.
Nos vemos, Adrián. Un abrazo grande. Un abrazo a todos
a
los que estuvieron ahora y los que van a ver esto en diferido también, sobre todo para entender que va a ser muy difícil aplicar a un trabajo remoto en esta empresa. Pero puede que se abra alguno igual. Así que bueno, nos vemos.